Welcome and thank you for standing by. At this time, all attendees are in a listen-only mode until the question and answer period. This webinar is being recorded and may be posted publicly. If you have any objections, you may disconnect at this time. Now I'd like to turn the webinar over to Ray Ellis. Ray, you may begin.
Hello, everyone. Thank you for attending this session. I think we have a really great session ahead of us. So we're going to just go ahead and just dive right in. And we're starting with Roy McKenzie. Roy, go ahead and take over.
Can you hear me all right? With all our rounds of testing here, hopefully things are working, but stop me if not. My name's Roy. Perfect. Thanks, Ray. My name's Roy McKenzie. As you heard, I'm here from the Coleridge Initiative, and I'm presenting some work that we've been doing with Nathan Barrett, Uni, and Katerina that you see there, thinking about how we can empower data science through code modernization. And specifically, when we start thinking about survey data and the processes that go along with survey data here at FedCASIC, how we can use modern coding techniques and modern coding ideas to, as it says, bridge the gap between innovation and efficiency. So obviously here we're all talking about survey data, thinking about survey data and what goes on with it, but I think very few of us are interested in data and survey data itself as a kind of end in and of itself. I mean, as fun as it is, and I'm sure we're all, data nerds kind of in one way or the other, as fun it is to look at data and explore data, especially in this kind of space of thinking about public data. It's usually for a purpose, for informing research that then can go on to inform policy and inform the way that we all do our work. And so I think a lot of times we just kind of assume this linkage there between survey data and research projects. We think, all right, we're getting this data, we're collecting it, we're doing this, and it's going to inform research, it's going to inform products, either kind of directly with researchers accessing that, or sometimes with kind of the middle step of creating a research use data set based off that raw survey data that people are able to access and analyze. But I think what we want to talk about a little about today is what's going on in this arrow in between. And that's something that could be called the analytical pipeline, the process of transforming that survey data into a usable format that is accessible and efficient for research. But I think, as we all know, what really is kind of in that arrow is code, and is often a lot and a lot and a lot of code. Now, I don't have to tell y'all, but it's worth repeating anyways, that bad code is bad news for data products and it's bad news for research. At the absolute kind of worst case scenario, it can lead to data systems or research use data sets that misrepresent the raw data, either that are imputed accurately, that have derived variables constructed inaccurately, and that aren't kind of conveying what was actually collected in that survey, or in some cases in that administrative data. And then that can translate on the other end into analyses that are wrong and are drawing incorrect conclusions from the data itself that aren't kind of, revealing to us the truth that we want to discover about the world. But even in the best case scenario, where we're maybe not getting all the way to kind of wrong results, wrong answers, all that kind of thing, it can still, bad code can still lead to work that is not transparent or difficult to reproduce. So I think we've all had that experience, or at least I know I have, of opening up a code file that was used to create analyses or used to create a data set, and it's thousands and thousands of lines long, and there's only like 3 comments in there, and you have to spend the next 2 weeks trying to figure out what's going on, which doesn't, give you a lot of confidence in your ability to do it correctly. Even if you're an incredible coder, that's a monumental task. It can lead to data decisions that are unclear for end users, so people who don't know how these analyses were kind of decided, what these kinds of decision rules actually translate to in reality. And then on the kind of, the more administrative side of creating research use data products, they can require a huge amount of manual labor to update, because every small change in the underlying data set has to involve changes in multiple locations in the code, a whole kind of suite of, updating going on, and often by just one person who's going through the work of maintaining this legacy code. So this is kind of, the issue that we want to think about and start talking about how we can address this, how we can make some improvement and start using some more modern ideas to create better code and better uses of our data products. There are 3 keys to addressing this that have been highlighted actually by some folks doing really fascinating work in the UK on the reproducible analytical pipelines, as they call it. And those are tools, capability, and culture. Under tools, the idea really being that in some ways, you can write code and create data products or analyses with a large number of tools. And in many ways, I generally feel like that, it's pretty ambivalent across those choices. A lot of tools can be used well or used poorly. But even still, it's important to think about using the tools that make it most kind of easy and most efficient to code and to write code in a good and reproducible way, that make it easy for analysts to reuse, share, and communicate about each other's work. And on technology platforms that aren't kind of legacy, aren't proprietary, aren't going to be going away, but that kind of are going to be continuous and sustainable going forwards, so that the work you're doing now in a certain tool or in a certain suite of tools isn't going to be lost in 3 years when we switch to something else, or when that package or software is archived, or any of those kinds of situations. Along with that, we have to think about capability. So analysts need to have the skills to do good and reproducible work, to use code in a good and reproducible way. This is not something that's easy. If it was easy, we wouldn't be having this conversation, because we would all just sit down and write beautiful and exciting code. But unfortunately, it is something that's really hard. And it is something that takes a kind of active effort to do. And so analysts need to be trained in that kind of way. There needs to be guidance about how to do that well, both kind of on the individual level and on the organizational level. And then finally, it has to be something that's built into the culture, because it's, even if you've got this training, even if you've got these kinds of tools, I think we all know also that it is very easy for this to go by the wayside as soon as you say, wow, we've got a really tight deadline here. We're really running short on time. Let's just put this code together. Let's make something that works. Let's do this quick fix. And then all of a sudden you do that 5, 10, 20, 100 times. And you've gotten back to the situation of having very tough and difficult and hard to maintain code. So it has to be something that's really prioritized, rewarded, and supported at a cultural kind of level within an agency. So these are all good kind of in theory, but how does this look like in practice? How could you start actually putting these ideas to work on a real data set, and because we're here at FedCASIC, on some survey data? So we've been working on a case study of putting these principles into practice, which is the ARMS survey data, the Agricultural Resource Management Survey, which is administered annually by USDA NASS, and then a research data product is produced jointly by USDA NASS and USDA ERS. So ERS reached out with us at Coleridge to partner on how we could update their processing code. At the kind of basic level, the idea of this project was, as we've maybe discussed, that there's 10,000 lines or however much of SAS code that's been being kind of built upon and maintained over the last 20 or 30 years. It's kind of used annually, but as I said, there's a large procedure to update it. There was kind of one analyst working on this. And so they started getting concerned about, the capability and the ability to continue to update this in a sustainable way. And so the kind of baseline ask for them was to start switching from SAS to a solution based in R and rewriting this code so that it could be easier to maintain going forwards and going on like that. But what we tried to do is take this and not just do a line by line rewrite and saying, wow, here's 10,000 lines of SAS code. Let's take that to 10,000 lines of R code. Because in my mind, that's not any better. Even though maybe now more people are learning R, it's still a little more accessible to some folks than SAS. It's still going to be super, super confusing to have 1 or 2 very, very, very long R scripts that there's not really any gain just from doing that. So instead, we tried to think about kind of modernizing the code and putting some best practices into place, and really taking this general approach of modular code. The idea of modularizing the code here is to split out the kind of smallest independent units of function in the main overall code into their own functions, their own scripts, to break them off and allow them to be a little more self-sustaining. So you can see it kind of illustrated here, where we started off with one, huge main.sas file with thousands of lines doing all of the processing at once. I've certainly written a lot of those scripts, so I hope you have the mental image there. And what we started to do, in particular for the ARMS data, because it is a survey data, and so it was much, much wider than it was long, so to say. There was, on the order of a few thousand variables, only for, tens of thousands of observations. And so what we started to think about was, okay, well, each variable itself in some ways represents an individual piece of processing. Either it's something collected directly on the survey and then maybe cleaned or imputed, or it's a derived variable created from other variables. But in a lot of ways, the formula for that variable should be independent. So if we're talking about calculating household size, all of the decisions about calculating household size should and could live in one place, in one function in charge of creating that variable. This is really, it sounds very simple, but it's a big game, because I think when we go back to this kind of main.sas file, you would see, all right, household size is modified in one place here. And then based on one condition, then, 800 lines later, it's modified in another location and something like that. And so as we were going through and trying to kind of trace out this code and do this update, we were running into this problem over and over again, that it was just very hard to figure out even how a variable was being produced, let alone to kind of rewrite that or clean it or document it. So we started thinking, all right, well, let's, first highlight all the dependencies. So everything that household size depends upon, and then put everything into that one kind of script and allow it to be self-sustained, where if we wanted to only create household size without doing anything else, we would be able to do that, to just run the script to create just that variable, and everything would work fine and independently. Then these small scripts work as kind of individual building blocks that are then combined into larger scripts that go and produce the full data set. But there's a lot of benefits from here. And I think the main one is kind of this idea of decentralization, of now, before, where it required one person or a few people who really had an in-depth knowledge of this kind of long SAS script to be able to find and understand where anything could be located, how anything could be updated. Now we're moving to this world where individual researchers can come and update the formulas for specific variables. If they, if I'm an expert on a certain value of production type calculation or something like that, I can work on that suite of formulas without ever having to worry about damaging something else in the code, changing something that I shouldn't, and cause some kind of issue. In that same vein, modular code also allows us to bring into this idea from the software engineering world of unit testing, and that being that we can write individual tests for each variable itself, so that if I am an analyst or a researcher coming in and making an update to a formula, I have a pre-built suite of tests to say, hey, suddenly this household size is returning, values that it's saying there's 150 people in this household. Something has gone wrong with this change that you made. Obviously, that's a pretty simple example, but it's this idea of being able to isolatedly test each piece of the code and know then that if something is going wrong, it's something with that particular function, and you know exactly where to go to address it and to understand if something is broken. This is more on, that's kind of the unit testing on the code side, but it also allows us to input a kind of warning system for, I think we all know working with survey data, sometimes you, for whatever part of the data generating process, the data collection process, get variables that, don't make any sense, values that you don't understand where that came from or how that got put in. And so it also allows us to implement a very similar kind of warning system for those odd values and flag that if manual review is needed to catch any errors in the underlying data. And then I think this is where it gets even more exciting, is outside the kind of code and testing part, this modular approach also allows us to really change how we think about documentation. So the current state of the documentation for the ARMS data was, as for most data sets, kind of one long PDF with data descriptions of a few different things, and then the Excel data dictionary saying, this is the variable, this is its label, this is how it's calculated. But of course, there were a lot of things about that very, very quickly, year to year, became out of date. As new variables were added, as formulas were adjusted, as items were taken on and off of the underlying survey data. So you were left with this kind of choice of either things being very out of date, or of spending a huge amount of analyst time every year on updating not only the code, but also then going to update all of the corresponding documentation. And it led to a place where continuing to document this data set in a very good and robust way really became pretty unsustainable and pretty a tough ask for USDA to carry out here. So our thought for working in this modular approach was to actually bring that documentation into the code. For those of you who've used Roxygen, the idea here is really just documenting those functions themselves for each variable. So if we have that household size variable, we are documenting that function in the way you would if you were writing software or anything like that. But in the same time of kind of documenting that code, you're also including the documentation of the variable itself. And in my mind, it's kind of, you have the code documentation of what is going on, how the actual processing is happening, as well as the variable documentation of kind of what should be happening, what the formula is intended to be, and what this variable is trying to capture. And by including both of those in the same place, you allow for the documentation to really be much more accurate, as researchers and analysts, as they're updating this code, have the opportunity to see, hey, either I'm changing this in a way that doesn't align with what this variable is supposed to capture, or I'm changing this in a way that we think is important, but I need to update this documentation right here in the same file accordingly, so that it's up to date and accurate. That, of course, is much easier to maintain. And again, the idea is that it's very decentralized. You don't have to have one person sitting down and writing documentation for 3,000 variables. You can have individual kind of groups of analysts who are subject matter experts on a specific set of variables or a specific type of computation, coming in and making those updates and doing those adjustments to the documentation, as they're the people who know best how that documentation should be captured. Just as a quick example of what this looks like, this is all kind of, fake code and variables, but it's, for me at least, much easier to see it in practice. So this is, for example, if we were creating this V1B variable, some kind of value of production variable, you might before have this as one line in that 1,000-line SAS code, but now we would have one script, v1b.r, which takes in the kind of base data set and sets it equal to whatever value on the input survey. Don't worry if you don't know R. This looks really crazy. It's not any real computation. It's just showing the isolation of that particular piece of processing. Then we put in this documentation right here in the same code, so in that same V1B script, and we can say, oh, this is the value of production off farm. This is the description of the variable. These are the inputs that go into it, and that's kind of a consistent format of documentation across all the variables we're talking about here. And what's really cool is because we're on the back end packaging all of this as an R package, setting everything up in that way, that when we run everything, kind of compile it and document it, it creates this nice PDF, or also you can do an HTML version of the documentation that automatically, for every variable that we've created, because we have separate functions for every variable, creates this nice, well-formatted and clean documentation file that can serve as an updated real-time data dictionary created by the actual analysts themselves. So I saw the 2-minute warning there. So just to wrap it up, how does this relate back to these 3 keys that we're talking about? I think on the tools side, it's obvious. From moving to SAS to R, it's moving from kind of a proprietary and increasingly legacy piece of software that represents a burden for analysts to learn, especially, and they can't necessarily access that outside of their institution or their environment, to open source tools that are undergoing active training and development, both in universities and in the open source community. It's moving from the kind of paradigm of long single script processing codes to modular code that is easier to maintain and is easier to kind of decentralize and share the burden of maintaining. In that vein, on the capacity side, there's previously this issue of having a single point of knowledge, one person who really was the expert about this code. And of course, it's great to have a person like that, but it also puts a lot of weight on a person like that. And so again, it's this idea of decentralizing the code base to share that knowledge and share that kind of burden of doing the updates and allowing for more review and responsibility. Then finally, on the culture side, modular code in that same vein also allows for easier implementation of things like peer review. When you have this kind of consistent format and separate isolated pieces of code, it's easier to come in and see, all right, I understand what's going on here. Does this formula make sense? Let's talk through this and check out that everything works right. and it leads to that shared ownership over code and documentation success. And right now, that's a shared ownership inside of USDA, inside of ERS. But I think the long-term vision here is to really expand this even further and start thinking about how we can make this kind of code and the analytic processing that's going into producing this research use data set available publicly in a GitHub or GitLab type environment, where researchers themselves can then come in and say, hey, I've noticed an issue in how this variable is being created. Let me submit a request, a change request. Let me start taking some ownership as well of this code and of this data that I'm going to be using in my research. So hopefully that's an interesting enough overview there. We want to thank our partners at USDA ERS for all their help on the feedback with this project. And then I will turn it back to you, Ray.
Thank you so much. That was really interesting. I'm really excited about modular code, because that's a thing for me. So I appreciate that very much. We're going to move right along to the next speaker and do questions at the end. But if you do have questions for Roy, you can go ahead and put them in the chat and he can answer them as we're going, or I will do them at the end. So we're just going to move right along now to Christopher Carino.
Hey, good morning. Thank you, Ray. I'm going to start my video. Okay. And then here, start video and share.
It's good. We can see it.
Great. Okay, thank you. Okay, so good morning. I'm going to talk about some work that I've been doing with trying to crosswalk industry classification codes. So I've used RDF OWL, a semantic web language, to do these crosswalks. And the ones we're looking at are NAICS 6, JICS, and then I6. So I'll go through what those are now. Okay. Okay, good. Hopefully that advanced the slide. Okay. So just to discuss why the motivation for this research and the landscape of this, there are, as I'm sure many of you are aware of and probably work with regularly, many different industry classification systems. NAICS being probably our most commonly used today, but there's many out there, many internationally, and many that have been labeled as standards, right? Even in their names. So I'll just go through some of them. The Standard Industrial Classification System, SIC, which was the predecessor to NAICS from the 1930s to the, I believe, early 1990s. And then from what I was able to find online, you know, really petered out in around 2007. But still in use for many lot of documentation and a lot of data out there. The International Standard Industrial Classification System, a UN standard, that is all of these are actually in use today. So I won't go through all of them, but I'll just kind of point out some of them. NAICS you're familiar with. JICS, the Global Industry Classification Standards, a little different from the others in that it is a private standard, right? It's a company that maintains that standard as opposed to a federal or an international organization. So that one's a little bit different. And then there's the harmonized system, used a lot with international trade. The Standard International Trade Classification, another UN standard. And then two things which I think are used a lot, you know, at census. I don't know how much beyond there, but the end use commodity category, governed by BEA, and the advanced technology products code list. So there's a lot of ways to classify business activity, right? And relatively finite number of businesses that are out there that we're classifying. So there's an interest in just being able to crosswalk if you are analyzing a data set that the businesses have been classified in one system to relating those over to others so that you could merge and work with multiple data sets. Okay. So the four that I looked at in depth with OWL in this study are the standard industry classification system, right? That predecessor to NAICS. NAICS itself, the Standard & Poor's one that I mentioned, the global industry classification system, and then the first UN one that was mentioned, the International Standard Industry Classification System. I put the versions up there. I think the bottom one, revision 4, was around 2007 as well. And as you look at these 3 different systems, right? 4 different systems for classifying industries, you'll see there's a little discrepancy, right, in what the level 1, level 2, level 3, what those levels are referred to as. NAICS has 5 levels from sector, subsector, industry group, industry, and sub-industry. But the other 3 all have just 4 levels. And you could see there the counts of the number of entries at that level. So say for 6, there's 10 entries in the first level of that code system at the division level. And then those 10 divisions are broken up into 83 major groups. Those 83 major groups are broken up into 415 industry groups. And then those are broken up into 882 industries. So the total number of classes in each classification system is shown there all the way on the right. And you can see there's a lot of discrepancy. NAICS is definitely the most verbose out of these 4, building on its predecessor, and there's other differences as we go through them, and I'll point those out. So those are the 4, though, out of that previous slide of about 10 that I looked at using OWL. Okay, so just a quick description on OWL. Obviously something that's very Googleable, so you could research more on the web ontology language, which is abbreviated as OWL, even though it doesn't, those letters don't really fall in the same order, but I guess it made a better acronym than WAL. So it's a semantic web language designed to represent knowledge about things and relations between things. So just a classification system, right? A way to classify knowledge on any given domain of area. And to do that, OWL breaks things up into either classes or individuals, right? So you're either a class in OWL, which is a set of things, and it could be hierarchical, right? When you think of like in a biology class where they classify living things and they're broken down by high-level groups at first, mammals, and then they break down to smaller groups underneath there, and then break down further, and you break all the way down. Those are all your classes, but then you do have individuals as well, right? And so if you have your dog in your house, right, that's an individual of that class of dog, right? So there's classes and individuals. And in this study, since just working with the code systems, right, 4 different classification code systems, all of them are treated as classes. So as we go through and we look at the 4 systems that I had just shown there, everything's treated as a class in a hierarchy. The individuals in this case would be like the businesses that would fall under that industry classification code. And there's no businesses that I show or mention in this presentation, just showing the classes in the class hierarchy. Okay, and so there's a concept of a crosswalk, right? And a way to map your classification system or your ontology via a crosswalk. And there's many different things that are published out there. Unfortunately, there were some that were published on crosswalking NAICS to 6 and crosswalking NAICS to I6, the UN standard. So using those two, I was able to load all of those crosswalks into our model. And when you do a crosswalk, right, in OWL, if you're crosswalking individuals, you would use the OWL same as relationship. If you're crosswalking classes, it's a little different and use the OWL equivalent class, right? So if you have two businesses that are the same, they'd be identified through a same as relationship. However, two codes that are the same in your classification system would be equivalent classes. Okay, so before showing the ontology broken out and with all the crosswalk in there, I just wanted to make a few observations. So one, as I mentioned from the start, NAICS, there's very well documented, and it's the only one of the systems to provide internal cross references. Meaning, when you look at the NAICS data on the census website, you could look at the list of equivalent classes, equivalent codes in NAICS, and there's a whole spreadsheet you could download, and I've uploaded that into the model that I'll be showing. So NAICS includes those internal cross references. You have to go to other websites for external cross references to other industry classification systems, right? And that's what I mentioned with the second bullet point, is that really going pulling in crosswalks from these other systems, and sometimes even documenting fully the other systems, because there's a lot of documentation in various spots. I had to go to multiple sources to do that. Whereas NAICS was pretty well self-contained. The ancestry of NAICS from 6 makes it easy for a crosswalk, and I guess that's why that one crosswalk is published. Makes it very easy to go from one to the other. Likewise, for the international standard industry codes, the UN classification system, there's a published list that crosswalks to NAICS as well. And using that, we were able to go from, if you treat like NAICS as like a hub and spoke, where NAICS is the hub and these other industry classifications are the spokes, you could get from one to the other just by going through NAICS, because there's so many crosswalks done to NAICS that it makes it easy to go from, say, 6 to ISIC, because you could just go through NAICS to do that. And loading in the cross mappings that I found online, was able to find over 3,500 mappings just between NAICS to 6 or NAICS to ISIC. So quite a lot of mapping between them exists, almost too much, and I'll explain that in a bit. So I explained this already, that since there's no direct crosswalk here available, we're able to generate that using NAICS as that hub, that common link in a hub and spoke. And then the last thing I was going to mention, and I could show this in the demonstration as well, is just that when NAICS is so well documented that there's so many internal cross references that are documented, that if you go to like 2 or 3 degrees of steps to get from one class to another, you're pretty much able to connect the entire classification system, right? So like the old example of 6 degrees of separation in NAICS, right? Everyone in the world is separated by just 6 degrees of separation. The in NAICS, it's much smaller, right? It's like every code is separated by really just 2 or 3 degrees of separation, and you can get almost to any of them. And it would be interesting to continue this study with a graph database where you could see those steps and determine at what level, how many steps of separation your network becomes too connected, that everything is related, and it doesn't really pay to identify, say, one business that's identified in one code as being also identified in another code just because it's separated by 2 or 3 degrees. You might only want to limit it to 1 degrees, or in some cases none. You might just want to stick with that one code that identifies that business. Okay, so let me see if I can pull up the Protege viewer in the slides here. I think I have to just I have to stop sharing here, and then I'm going to reshare. And let me see if I can do this. Okay. Hopefully it's here. I'll maximize it. Okay. So you can see here using this tool that I broke up. See, the OWL breaks up the whole world that just considers things. Whatever's a thing, you could classify in OWL. And so we did an industry classification system, which is a type of thing. And then we have 4 types of industry classifications that fall under that heading, right? So for each one, then you could go in and go through your level 1, level 2, level 3, level 4, which I had shown before. You could see NAICS here. This is the 6, the Standard Industrial Classification System, the UN Standard, International Standard Industrial Classification. You can see how they all differ a little bit, right? There's a lot of commonality here. Right? I mean, just looking here, you see agriculture, mining, agriculture, mining, agriculture, and mining, right? So there's a lot that should be crosswalked between these. And then the global industry classification, which I mentioned before, is the one that's private. It's not a government organization that is governing the standard. And it looks a little bit different, but you could see it's similar in ways as well, right? And as you break down through things, you'll see it starts looking very much like the other systems. Okay, so that's just loading in the classification systems into OWL, establishing the hierarchy. But let's now look at the cross references. So when you go to these different sites, you can identify cross references. There's a lot of already ones that are documented, as I mentioned with NAICS. There's some that are even right on the Census Bureau website. And let's just go down the very first bullet here, agriculture, forestry, fishing, and hunting. Click under there. As you can see with NAICS, the next level is here. I don't remember exactly what it's referred to as. This could be the subsector, I believe. And then the industry group. And then I believe it's just called the industry sector. Not exactly sure of the level, but we keep going down. And then when you get down to the final level, you'll see, I guess we go here, the icon changes a little bit. And what you're going to notice is that the standard 6 subsectors are all there. Apple orchards, grape vineyards, all under that, under non-citrus fruit and tree nut farming. But you see these equivalent relationships. And what those equivalencies are the equivalency to the other classification system. And so apple orchards in NAICS 111331 is equivalent to 0175 other non-citrus fruit farming in the UN code.
Hey, Chris, can you wrap up here pretty quick?
Sure can. Yeah. Yep.
Thank
this
you.
is it. So you can see those relationships there. And what you also notice is that the breakdown, once you create an equivalent relationship, you've now pulled the other industry classification system into your subtree. So grape vineyards, growing of grapes aligns with, is now pulled in, even though it's not in NAICS, it's showing up there. So the crosswalk is complete. And if we had individuals of businesses, you'd see them now classified as both. So that was the demonstration. And then I'll just wrap up and summarize. There's a lot of interesting things you could do with these crosswalks. As I was mentioning, you could create crosswalks that don't exist published out there. And you could also really analyze how effective they are. As I was saying, if you have too many connections, it's not as good of a thing either. So I'm going to close out here, but any questions, please put into the chat. And thank you for watching.
Thank you so much, Chris. We're going to move right along to Stuart Jollymore. And I'll pull your slides up right now, Stuart. So.
Thank you, Ray. And I do apologize to everybody for technical issues. I do not have my webcam on today. But a quick intro as Ray shares my slides. My name is Stuart Jollymore. I'm a data scientist with the Defense Personnel Analytics Center. So that's basically a subdivision of the Defense HR department, which is Defense Human Resources activity. And DPAC is the owners and the creators of a lot of survey data. This is not our first time presenting here at FedCASIC. We always love doing these data science lightning rounds. So it's great to be here again. So today I'm going to be discussing or giving an overview of a PII removal tool that we built for our survey comments. So Ray, next slide. Why do we remove, or why would we want to remove PII from our survey comments? There's a number of different reasons for this, and that makes the tool that we ended up building so useful. Our surveys that we do are anonymous or at least confidential. And oftentimes people can leave information in open-ended text responses that could be used to either identify them or other personnel that they are discussing. And since we have anonymous and confidential surveys, we want to ensure that we scrub that data out before we share these comments with, our stakeholders, some of whom are sponsors of our surveys. We have the DOCS, which is a big climate survey, and these comments go back to their unit commanders. So if you can think about, leaving a open-ended survey response with respect to the climate of your organization, and then them reading those directly, you can see that, especially on smaller units, that information could quite easily be traced back to you. So all of these scrubbings are done by hand at this point, and it's quite a laborious process. Our surveys have between 6,000 to 10,000 open-ended survey comments, and the DOCS, which is I think collects 1 million survey responses a year, and the turnaround time to unit commanders is 72 hours. So you can see that, it's basically impossible to do. So we wanted to build a tool that allowed us to do this automatically. And so what we used is name entity recognition for entity extraction. We used the SPACY library, right, the SPACY pipeline for this. And we trained our own models on some of our own entities that are not in, the off-the-shelf SPACY models. Next slide. So just to give you a conceptual overview of what our process looks like. So we collect our raw survey comments, and then we import our saved model that is stored on GitLab along with the code needed to run the model. We apply these functions and these models to the raw survey comments, which identify the PII, and then a new column, and then we apply a cleaning function basically that uses the information that SPACY attaches to each survey comment. And we use that to basically string replace, if you will, those entities that our model has detected as being personally identifiable information. And then lastly, a new column is created, and the PII again is redacted, and then that data is then added into our tables, survey tables, and then can be disseminated a lot more widely than we would want the raw data to go or to be disseminated. Next slide. So our training set, so we trained our own model, right? We have some entities that are unique to our domain. And so we needed to train our own model to identify these. And basically what we did is we took 180,000 previously, or 180,000 comments, both the raw comments and the cleaned ones that had been done by hand. And we basically back extracted using the raw comment and the clean comment, all of the entities that had been redacted, which was actually kind of a tricky process. And I think we only were able to get about 90% of usable ones, between 80 and 90% of usable ones, because sometimes you're redacting some phrases, or you have several things you're redacting in order, like in a row. And so because of quite a hard process to like go back to the original once it's redacted. So at the end, from those 180,000 comments, we were left with about 20,000 examples of redacted identities that we could use for training purposes. And then, I'm not sure how many people here are familiar with FACI, but basically what you need to train FACI is the comment, the mask, right, or the label, what you're going to redact it with, the start and end position of that entity that you're replacing, some link to the comment, right, here it's comment number, and then the masked entity, right, so the thing we are determining as to be PII. So those are kind of the inputs into the training data set. And then we proceeded with training. Next slide. So some of the custom entities that we included, what we actually found out is that we could do better than the FACI out-of-the-box model could on dates. So we trained our pipe, like our custom NER model on date, enlisted ranks. So these are like, sergeant, private first class, and then all possible slang terms, right? So the one I always give is for gunnery sergeant. No one typically says gunnery sergeant, so the slang version is gunny. So those are all in there, officer rank, locations. Now, FACI out of the box does have a pre-trained entity recognizer for locations, but it doesn't always grab the things that our hand coders have been trained to identify as locations. So sometimes these are bases or other entities that may be missed. And we did find empirically that putting this into our own identifier yielded better results. And I'll address why that might be in just a minute. And then expletives, we do clean these for bad words. And then medical, right? And these are, health-related issues that can easily be used to identify a service member or a respondent on our surveys, especially at the unit level in our DOCs. So those are the custom entities that we trained. Next slide. Right, so how did we do, right? So one of the things you have to note about NER models is we don't have kind of like the traditional metrics that we might think about when we think about prediction models, like accuracy or area under the curve, et cetera, et cetera. And so like kind of the go-to metric for evaluating an NER model is using either precision, recall, or F1 score, which is the harmonic mean of precision and recall. We ended up using recall to optimize our models. And the reason we use recall is that allows for a greater, or it reduces false negatives. That would be PII that exist in the text that was not identified. So precision measures that, but recall basically allows you to redact more information with the certainty that you're getting more of the actual PII that exists. And the downside to that is that you end up redacting more. But since we're here to protect people's identity, we'd rather be more conservative and redact more of the comment than expose people's identities to commanders or other analysts, or just if and when this data gets into the public, things of that nature. So that's why we chose to do chose to optimize our models on recall. Date, we did very well, right? So we had a recall of 91.91 or 91%. Location, E rank, O rank, and expletives were all in the 80s. As it turns out, these are actually kind of a little bit antiquated recall scores. We did some more tuning of our models, and we're also going to get more data in the future. So right now, I think location, E rank, and O rank are all in the mid to high 80s, which is a lot better than we had expected just by tuning some of our models, right? For emails, phone numbers, social security numbers, websites, etc., we actually just use regular expressions to extract those, because those all follow a very predictable structure that are easily detectable using regular expressions. And then we continue to improve our recall and our model redactions. And as I said, we're going to be implementing more data, tuning the back-end models that I can describe briefly. Closer to the end, I want to make sure that I get through all of this before I get too far into the technical weeds on stuff. And I think for cleaning purposes, I think once the model is loaded into memory, I think we cleaned 1,000 comments in, I don't know, I want to say like 2 or 3 seconds, which is vastly faster than a human could do it, and really is well suited for our use cases, especially with respect to the DIOCs. Next slide, please. So after all the machine learning is done, which is really like the most laborious part, the function to redact our or to like make these calls is really quite simple, right? So here's our function that does the cleaning. Like as you see, it's just a few lines of code. Of course, there's like 2 transformer models that are sitting on the back end that do some of this pre-processing, and those are housed at the model path. Again, you see this is actually part of a larger Python class. If you recognize Python, you'll see self-dot a lot in here. So that's a dead giveaway that this actually fits into a bigger processing scheme. But this is just the redaction part, and it's quite quick. As we said, just processing 1,000 comments in just a few seconds. Next slide. And then we have some example entities that I probably won't go too far, too closely over these. For those who have interest in kind of reading through these, you can kind of take a peek as I'm talking. So I'm going to use the remainder of my time to kind of discuss some more of the technical aspects of what the training process looked like, what we're using, and be a little more explicit about the back end. So as I said, we use FedCASIC library, which is a very competent NLP pipeline framework for doing a number of NLP tasks. And for our custom entities to identify those, we actually use the domain adapted BERT model as the back end. So our transformer model architecture is the BERT base cased. And then we trained that on our we trained that using mass language modeling. So we used a large number of survey comments to basically inform that model of how our domain uses language, which differs a little bit from what the training data for BERT is. And so that's the back end, right? And then from there, once we have that domain adapted BERT model, we use that in the back end. So basically just pointed basically to the location of that domain adapted model in the config file, and then trained the custom entities using that back end through SPACY version 3, which is all the command line coding, using the config file, which is like a huge improvement over kind of like SPACY v2 for anyone who's familiar with the SPACY coding paradigms. And we trained this on a Tesla T4, which is just a 16 gigabyte GPU. And I think training takes about 45 minutes using the BERT-based cased domain adapted backend model. And then that's what we use for our custom entities. Now, when it comes to putting this back together with SPACY, what we end up with is a SPACY model, but there are other entities we may, that from the pre-trained SPACY models that we may want to implement. So the nice thing about SPACY is that we're actually able to just drop this like fine-tune model, right, for our custom entities into the SPACY pipeline. Because it was built in SPACY, it just drops in as another item in the pipeline. So what we get is we can run our data through the pre-trained off-the-shelf web core transformer model that's pretty powerful, and we have access to all the pre-trained entities there. So like locations, names, which is another thing. We didn't talk about names here, but we have that's how we extract names, by using the pre-trained one. And then once those the comments have been run through those, then they run through our custom entity identifier. And then at the end of the day, we can determine in our cleaning process which entities we want to redact and which we don't, which makes it a little more customizable for surveys that maybe we want to redact more information or less information depending on the use case. I think I have to wrap it up. I think there may be 1 or 2 slides left at the end here. So I just wanted to say we did this project started off with a basic dictionary lookup. So we took all the entities that had ever been redacted, and we used that as a lookup dictionary, and then just, if it's there, redact it. If not, leave it alone. And these are the recalls that we got. So date was about half as good. Location was a little bit better than half as good. E-rank did fairly well. O-rank did poorer. Expletive did poorer. Medical did poorer. So there are big gains here to do over just like a lookup dictionary. So we do a lot better here. So that's the good case. And the reason the recall is so bad is that it just misses a lot of them, right? Just as a reminder about how recall works. So that sums it up. Over.
Thank you so much. We're going to go right into Evan Nielsen now.
I'll actually kick it off. Good morning. I'm Marissa Pelzer, a program analyst at the Institute of Museum and Library Services. My colleague Evan Nielsen from the American Institutes of Research and I are presenting today on the Public Library Survey and our recent methodological initiatives. For those not familiar with IMLS, we are a small independent agency that is the largest federal funder of libraries and museums in the US. And our goal is to advance, support, and empower America's museums and libraries and related organizations through grant making, research, and policy development. My office, the Office of Research and Evaluation, we manage the Public Library Survey. Next slide, I'm sorry. Which is an annual census of all public libraries in the 50 states, DC, and outlying territories. States collect the data on their public libraries and their state surveys within their jurisdictions, and then share them with IMLS through an online web portal. Most of the PLS data is collected at the library system or administrative entity level, including data on finances, collections, staff, and services. There are over 9,000 library systems representing 17,000 points of service, or in PLS parlance, outlets associated with one AE. We pride ourselves in our amazing response rate. We annually get over 95% of our AEs. And what we do is we take our data file, and every year we append geospatial information to both the AE and outlet data files. And that's a full range that Evan will go into next. Next slide. Just to show you kind of the breadth and spatial representation of libraries across the US. These maps show the location of the systems. The size of the dot shows the difference, the size of the population that they're serving, and then the color denotes if they're in a rural, urban, suburban, or town area locale. So the next slide. Our goals for the research, and I love that this ties into that first presentation where we kind of forget that middle piece. Our goals for research with the PLS are to follow the national, state, and other subgroup trends, provide peer comparisons, provide the data for peer comparisons for strategic and operational planning of individual public libraries, and then more challengingly, document the value of public libraries to their communities. And next slide, I'm going to soon pass it over to Evan. Over the last 5 years, we've undertaken a set of initiatives to try and improve the methodological rigor and utility of the PLS data. We took control of the operation, I shouldn't have put it in there, operationalization of data elements through stakeholder engagement and adding rigorous cognitive testing in the field. And that allows us to release the data element definitions to the state respondents 6 to 9 months earlier than we did previously, which allows them to roll it out at the state level, which increases our first year response rates. And with that, I'm going to pass it over to Evan to describe a little bit more about the geo location work that we've been doing.
So some of the challenges that we've encountered in the last several years related to the geographical attributes of the libraries in the PLS are on this slide. The first is that each library jurisdiction or AE, as Marissa explained, service area has a population that's reported by the state agencies in the PLS. But we've determined through various efforts that the sources that the states are using to determine those service area populations vary. Some of them are using decennial census, and so they only get updated every 10 years. Some of them are using the annual population estimates. Some of them are using ACS estimates. Some of them are using state data centers that might use some census data, might use some other state demography or vital records information, all that kind of stuff. So the effect here is that these affect the per capita metrics that are released by IMLS. So it's difficult to compare state to state if the denominators in per capita metrics are based on different kinds of sources. The other thing is that the geographic coordinates of where the libraries are, and then so that's the only thing that's on the file currently. And then there's also outdated qualitative jurisdiction indicators. There was previously, and so we know that library locations exist within multiple geographies, right? They're in a county that's also within a township that's also within a municipality or a school district. So it would take data users a lot of effort to try to identify using the existing data and join those to other geographies if they wanted to join the PLS data to other data sources that have some kind of geographic dimension. On this slide is a big table. What I want you to notice, though, is that as the population size of libraries increases here, the number of public library systems decrease as you go up this second column here. But the number of outlets in this fifth column here is largely stable. And so the takeaway here is that the larger the service area population of an AE, the more outlets there are in those AEs. And basically that means is that if you wanted to do any kind of analysis of what's happening at a local level in the larger population centers, in those urban and suburban areas, this is really hard to do with only administrative entity level data. And as Marissa explained earlier, most of the data that is collected in the PLS is at the administrative entity level. There's not a whole lot of data that we collect currently at the individual outlet level, which is that sort of point of service. So all of this is background and context to some research that IMLS was directly or indirectly involved in recently that didn't quite turn out as expected related to those challenges I mentioned earlier. So the rest of the presentation is basically just kind of explaining sort of the details of those issues that we ran into and how we're trying to mitigate them going forward. So first, Lisa Freehill and Melissa Sedade linked PLS data with American Housing Survey data from 2013. And substantively, they were looking at the relationship between library use and collective efficacy within a community, which is actually, I think, an interesting research question. But I'm not going to get into the details of what they shared there. There's the, when the slides go out, the link is there if you're interested in that research effort. Shortly thereafter, IMLS and AIR attempted to link the National Household Education Survey data from NCES in 2019 with PLS data, trying to look at the relationship between different library measures, especially those related to children, and whether or not households with children visited the library, which is based on a self-reported indicator in the NHES. Controlling for demographics and also for distance to the nearest library, the nearest local point of service. So both of these research efforts ended up with some major caveats in their findings. Both of them were basically taking library system level data, the AE level data, and attributing that or apportioning it somehow to the outlet level, and then linking those outlets to the other data source records based on a location. In both cases, they were the location of a household or the proxy location of a household. And so both ended up with substantial caveats in the findings because of both the spatial join used as well as the attribution of the AE level data to the outlet level. And for example, the NHES and PLS study did find some statistically significant correlations, but essentially there was significant concern or major concern that the results would be misinterpreted because of the convoluted way that we went about doing the linkage and attribution sharing of data between the levels. So there's sort of two major risks that I'm going to talk about and how we're mitigating them based on these results. So, and you could probably guess where I'm going with this. So the first is just inaccuracy. And that is that linking a household to the closest library outlet may not reflect the outlet that household actually visits or would consider visiting if they didn't actually visit it. or even whether the household is located in the service area for a given library system. Just because it's the closest one to them doesn't mean it's the one that they have a library card for. So one of the ways that we're trying to mitigate this is by updating the geographic identifiers that we put on the file, which Marissa mentioned earlier. And so the first step to this is already implemented, and that is revising the geocode category options. Geocode is the name of the variable in our file that indicates that what the geographic area is that aligns with the service area of the library. And so one of the things that we had to do is separate places from minor civil divisions, because previously that was just one category, and then adding multi-place and multi-civil division categories, and then separating school districts, which was previously one category, into the 3 different levels of school district boundaries that are available from NCES and the Census Bureau. So this change is allowing IMLS to include different geo-IDs, census identifiers, for most of the library service areas in the FY22 PLS data files that are going to be released very soon, within the next month or 2.
Within the next 3 weeks.
Oh, there we
2
go.
weeks. Yeah, I'm excited this year. It's
Hot off
early.
the press. And so what we're hoping then is that by including these geo-IDs on the data files for the library service areas, it will make it much easier for data users to link PLS data to other data sources for those same jurisdictions. Much easier than it was in the past, when there was simply just a point location or maybe a census tract ID. Now there'll be an easier identifier for the service area to link to other geographic data. The other risk that we encountered with this is basically one of bias related to how we're attributing AE level data to a library outlet, and especially in larger systems, which, as I mentioned before, tend to be in those urban and suburban areas. And so by just what the methods that we've used in the past were essentially a proportional approach based on, for example, square footage, but that it's just an approximation, and it has the potential to mask real neighborhood level variation between outlets. And so in order to try to address this, something that is still, we haven't finished, is in progress, is exploring collecting outlet level data in the PLS. And so what we know is that libraries are already tracking a lot of the current data elements that are reported at the AE level. They're already tracking them at the outlet level so that they can add them up and report the system level number, for example, the number of visits to the library. And some of the states that are reporting to IMLS are already collecting these at a state level in their state surveys. And so we are currently conducting cognitive interviews, and we're going to be running a pilot with one state to implement this change. And we're also planning to conduct a respondent research survey to kind of understand the mechanics of how we can implement this change. And the goal, what we hope, is that by collecting this outlet level data, it'll make it a lot easier for data users to analyze PLS data in those areas where there are a lot of outlets in a given jurisdiction at a neighborhood level, which could allow joining with more small area data sources. So a few next steps that we have in mind is that, one, IMLS is going to continue to refine the service area geographies for as many AEs as possible, particularly the multi-area. So we're trying to figure out the best way to structure the data file when there are, for example, a library service area that covers multiple counties. What's the best way to structure how to put those geo IDs for the different counties involved on the data file so that it's easy for to explode those to sum them up for analyses. The second is that IMLS is considering formalizing the collection of state-level shapefiles of library service areas. The main impediment here is that not every state has such a shapefile or has plans to create one. And so even if IMLS move forward with this effort, it may result in a non-exhaustive national shapefile of library service areas, so it still wouldn't sort of solve the entire problem. That's actually it. But we'd love to have any advice that you have if you've dealt with a similar issue on any of the surveys that you are familiar with, or you know someone who has. We would love to hear from you how you've approached these kinds of things, and our email addresses are here.
Thank you so much. That was really interesting. We're running out of time, so we're going to quickly go on to our last presenter, Sun Lee.
Okay, can everybody hear me?
Yes, and we can
Okay.
see your slides.
Okay, great. Okay, let me start. So it is really interesting to see how all these data science applications are being used. So let me just, I was Googling, what is a data science? So my quick summary of it is the study of data to extract meaningful insights. So in this context, typically a data science field goes through this like 5 stages of life cycle. However, my talk today is going to be focusing on this data processing and analyzing aspect of the data science. So like here's a roadmap. In the time that I do have, I'm going to start with how machine learning based record linking really works. So as you can see, the machine learning based record linkage that I've been doing is a supervised algorithm. Basically, it's a fancy way of saying that we do need a training data that has typically a pattern of what is a true match and what is not a match. And a high quality training data could lead to a highly predictive performance of an algorithm that about unseen data. So for example, in our context, if a high quality training data shows a pattern of these are individual patterns of match and non-match of 2 different data sets of individual level data. That could be one is a survey data and the other one is administrative data, and then high quality training data based on that. And then we can actually predict what is a linkage, what is a true match or not based on this high quality training data and algorithm. I'm going to focus on random forest classifier, which is a type of machine learning based record linking implementation. I would like to say that, for example, IPUMS has implemented another implementation of ML-based record linking, such as Support Vector Machine, or Ancestry.com also has implemented mainly XGBoost-based record linking algorithm. Then why RFC? I like it because of it's very accurate and it's very scalable, meaning that, the previous talk also has mentioned about, and keynote speaker has mentioned that it is very costly and then how to cut corners. And one of the really high cost aspect about the record linking, especially about the big data, is the computational time and computational resources that it takes. So in that regard, RFC has a lot of attractive features because of its accuracy, scalability, and ease of tuning. I don't have a lot of time, so I'm going to just get to the gist of it. Then what type of record linking that I have done so far? So let's actually take 1 minute what are the roles of immigrants in understanding the American economic growth during the late 19th and early 20th century, when the US essentially transitioned from a largely rural nation to the technological frontier. So for us to really measure the role of immigrants, we need following data sets. So big data, 3 types of big data, And we also use machine learning to link this individual level data. One is several waves of US population census starting from 1880 to 1920, but it is really universe of everybody who appeared in the population census. Second, that it's the universe of US patents during the same period. Who were the innovators? Who were the engines of new ideas and growth and innovation? To do that, and also thirdly, then what kind of special human capital or knowledge that immigrants must have brought with themselves? It's like embodiment of knowledge when they came. So, what's really nice about the third type of immigration data set that we use is that it also lists their pre-migration occupation, meaning that if we see Einstein, for example, or other scientists, it's not just we see their names, but we also see their pre-migration occupation, whether they were physicist, mathematician, or factory worker. And therefore, by combining these millions and hundreds of millions of data sets at the individual level from both each data source, we are going to construct a very large data set. So as you can see from this slide, basically blue, the population census, green, the historical patents that list basically the inventor's name and location, and what kind of ideas that they invented. And thirdly, as I mentioned briefly, that immigration records that they list name and age, but also nationality, whether they were Italians or Germans or Irish, but also what they were doing as a primary occupation before they migrated to the United States. Here are the final data sets. So we, out of about 100 million, and let me make a quick note. In this male, so caveat, so in this audience, I want to be very clear that we unfortunately could not link women's records due to last name changes. I do think that this is one of the last frontiers that we should be able to work on with additional data sets and digitization of those, such as marriage record that also captures how women's last name changed and the year of marriage and things like that. But something that we could do is potentially with the additional digitization. And I also would like to make a quick note that 3% of US historical patents at the time were invented by women. So this is a very important next step. In any case, we constructed this humongous data set that captures both foreign-born or US-born patents, because patent data alone without linking, we do not know who were the innovators. We may see the inventor's name, but it is unclear whether they're US citizen or they're immigrants. If immigrants, what type of, what is the nationality of those people and when they immigrated? Where did they immigrate when they were very young, or they immigrated when they were adults, when their human capital from the old continent were already mature? There are a lot of questions. When we are doing this, there were a lot of data science applications on our end as well. So I heard during the previous talks about the implementation of SPACY. We did the similar thing, and we also did a lot of crosswalk of industry categorization, that how certain patent CPC code would map into the Census Bureau's IND Industry 1950 code, or things like that. So it is really exciting to hear all these applications. In this context of linking immigrant and census records, they primarily use their name and age and nationality. Here are the potential concerns. I don't have a lot of time to go through all these, but I would like to quickly note that, a researcher should think very carefully that how immigrants may choose to anglicize their name at some point. And similarly, if you use very foreign name, then even if you have the really good training data set that now trains based on the handwritten records, still it is well documented the mistranscription errors for these very foreign names are much higher. And also, very common name, like John Smith. how would you ever find and link the John Smith living in New York or things like that? All these potential concerns still apply. So also, beyond all these concerns that I just mentioned, I also would like to note a quick aspect on what is another layer of record linking challenge and its application. In another working paper with Professor Brendan O'Flaherty at Columbia University, and myself, we are also tackling these issues that who are the descendants of the enslaved people to find better or worse ways to implement reparations. So the key question here is how the data linking between, the slavery records and then that really lists the historical class who should receive the payment if they had been alive. But what we have now, that happened 150 years ago. So then what are the ideal people, the descendants of those enslaved population? However, even if the record linking is done at its finest, however, the issues still issues of false negative and false positive of people who shouldn't be there was classified as, they are the descendant, or the false negative, that the true descendant who should be there as an ideal contemporary class and therefore qualify for the payment, they were not included in the data. How to really think about this? Yes, 2 minutes, thank you. So these are really important aspects. Well, I don't have a lot of time, so let's go to the 2 minutes. So, one of the aspects is what is the best practice of doing the record linking? This is a really hard question and the trillion-dollar question because we don't have ground truth. Typically, many of the data sets that we would link, whether that's historical or not, or modern, it typically does not have like social security number or things like that in at least one of the data sets that we would like to link. So what we did, our take on this is at least compare the performance of RFC with existing models or methods that are widely used, such as iterative record linking. I will share the slides so you can actually go over this very carefully. But quick thing that I would like to note is this is great. However, let's note that iterative record linking still has a very low recall rate, which could be a drawback depending on your research project. Another methodology, which is ML based but unsupervised, meaning that you don't need a training data set. Well, it's another great way of implement the record linkage using machine learning. However, it does not require a training data set, but it is very extremely costly in terms of computational time. So in any case, we were comparing a bunch of things such as, okay, in the absence of ground truth, how you should think about it. So we were also visualizing the Venn diagram to really compare how much there is an overlap among different methods of record linking or descent across different methods. And also, what are the distribution look like depending on the algorithm compared to the cross-sectional data, things like this. So, let me wrap up. So already there was a lot of discussion about precision and recall. So let me just show you that what we do essentially is we always try to tease out information that we never used in record linking criteria. However, it is available in both data sets that we would like to link, and then see whether there is a lot of harmony or consensus between two different sets of information that's independently collected. Let me conclude, let me take stock. So unlike the Bailey and her co-authors paper on automated linking and the performance of it, I would like to say that automated methods perform fairly well. And however, maybe what you could do as a researcher is try to always find ways to validate the accuracy of those matches and how it may have different type of distribution or different types of matches compared to other existing record linking methods. Okay, here it is, and thank you so much.
Thank you, everyone. We're sort of basically at time, so we don't have time for questions, but let's give one more round of applause to all of our speakers. That I think this was a really great session. If the slides are going to be made available, and so if you want to follow up with questions, email addresses will be on those slides so that you can follow up. And thank you, everyone, and we hope we see you in later FedCASIC sessions today.
Welcome and thank you for standing by. At this time, all attendees are in a listen-only mode until the question and answer period. This webinar is being recorded and may be posted publicly. If you have any objections, you may disconnect at this time. Now I'd like to turn the webinar over to Erin Boone. Erin, you may begin.
Thank you, Lisa. Welcome everyone to our roundtable, NLP in Practice, Applying Natural Language Processing to Survey Text Data. Over the next 90 minutes, we're going to discuss a few NLP projects at BLS, but we're going to focus less on their specific methodologies and more on the shared logistical challenges that projects like these face as they move from research into productionized tools. Before I get too far, I'm going to take a quick moment to define natural language processing, that we're going to say NLP from here out. I don't think any of us are actually going to go through that whole mouthful every time, but essentially it's any model that's based on human language, right? So typically that's text data as opposed to numeric or image or some other kind of data. It could be speech, sound data. It's a very simple and broad definition, but it's a broad set of tools and applications, right? So it might be machine learning based, so a statistical model or a deep neural net type model, or you might take a rules-based approach, which is also NLP. Basically, it's NLP if you are working on a problem where the data is human language. So tasks like speech recognition and text-to-speech, when you talk at your phone and it talks back to you, right? That's NLP. Document classification is a very popular one. A couple of our examples that we're going to talk about today sort of fall into that bucket. Document summarization, information retrieval, topic modeling, named entity recognition. We heard about that in an earlier session. Text matching is another one. Machine translation, right? Google Translate, that's NLP, right? And many, many, many more, right? So you can see there's tons of cool applications with human data, or human language data. It's very difficult problems that we're working on. The panelists are going to introduce a few projects that fall under this NLP umbrella, right? Again, not to highlight the modeling approach, but to use them as examples in the complete NLP product development cycle. And we're going to expand on what I mean by that. We think there's lessons here that can be applied to NLP projects in any of those applications. Right, so to set your expectations a bit, our discussion will be about the logistics of a successful research project, right? Developing a prototype or a proof of concept model in collaboration with stakeholders and others. And then moving from a proven model into a production environment and all of the requirements that come with deployment, ongoing maintenance, et cetera, right? So it's a whole thing, whole apparatus. So the agenda is very basic, but we're going to start with some intros. I'm going to give a brief bio for each of our panelists so you can see also on screen, I'm hoping, although I don't see what you see. But each of our panelists are actually going to sort of set the stage for themselves by taking maybe 10 or so minutes, 15, to introduce an NLP project. Then we'll have a bit of Q&A with questions from me. And then we're going to leave at least 20 minutes for audience questions. So as we're going along, think about questions. You can definitely drop them in the chat as we go. And we're gonna see how it goes. It might go a little sort of loose and stagger between questions from me, questions from the audience, depending on what we're seeing. But we'd really like this to be more interactive. So please do have some questions. Don't be shy about raising your hand. There's an opportunity also for you to raise your hand and we can bring you off of sort of mute or off of camera mute, whatever. Now we'll leave your camera off, but you'll be able to come on and speak your question yourself if you'd like to. So hopefully you'll have questions. So who are we? So myself, I'm Erin Boone. I'm a data scientist in the Office of Survey Methods Research at the Bureau of Labor Statistics. I've been at BLS just since the beginning of 2023. Before that, I was a data scientist in the digital publishing industry, online news specifically. I came to data science after doing a PhD in linguistics. So I've been working with language data for quite a while. Our panelists are colleagues of mine at BLS. Amy Thompson is a member of the data scientist team in the Office of Prices and Living Conditions at BLS, and the lead data scientist for the Consumer Price Index Housing Address Matching Project. Prior to joining BLS, Amy worked in academia and the national labs on machine learning and natural language processing projects. Melissa Pollock. Missy is an economist in the Office of Prices and Living Conditions, also at BLS, and is the product owner of the Consumer Expenditure Diary Survey Autocoder, responsible for the product strategy, stakeholder management, and delivery. Prior to joining BLS 2 years ago, she had a long career leading global analytics and data science teams in the private sector, largely in the marketing space. Her primary interests are using data and analytical and data science capabilities to make better and faster decisions in an intuitive way. And then Danny Todd, you can see I'm struggling with the nicknames. Daniel Todd. Danny is a data scientist in the Compensation Research and Program Development Group and is the product owner of the, I'll say it once, the full version, the Survey of Occupational Injuries and Illnesses, aka SOI Autocoder. Prior to joining BLS a year and a half ago, Danny worked in the private sector as a machine learning engineer as a defense contractor, primarily for the Navy and submarine force. So the ordering of our faces here is logical. The example projects that each of our panelists will introduce each represent a stage of the NLP product development cycle. So Amy's going to start with a project that is in sort of a research phase. Missy's going to introduce something that's in a kind of V1 product launch phase. And Danny's going to talk about a mature model that's been in production for a while. Right, so that's the order we're going to take. And as I said, we're going to kick it to each of the panelists. They're going to sort of intro themselves, a little table setting rather, with the project introduction. And we're going to start with Amy, and give me a nice cue when you want me to change slides.
Okay, will do. Can you hear me well, Erin?
You're a little faint. I don't know if you could be louder.
Oh, okay. Hopefully that's better. All right, I'll be speaking with you today on a research project with the Consumer Price Index, having to do with the housing team and address matching, so string matching, if you will. Next slide. So just a little bit more about the team that I work on. It's within the OPLC, Office of Prices and Living Conditions, but we have the opportunity to work with many different programs within OPLC. And so the research, especially the NLP research that we get to do varies quite a bit, depending on the program and also the indexes. So for those of you not quite familiar or as familiar, things like the Consumer Price Index, Producer Price Index, the imports and exports, and also consumer expenditures. And Missy will say a lot more about the CE program later. Next slide. Thank you. So this is a relatively new data science team, and we're tasked with working with the economists and statisticians within these programs to work on and improve their outputs as possible. And at the bottom of this slide, you can see just kind of a brief listing. There's definitely more. This is not exhaustive of the types of projects that we've worked with the different program offices. Next slide. And I narrowed it down just a tiny bit. These are ones that I would say, I could say all of them have NLP components to them, but I think these were more specific, like felt more NLP to me. And today, let's see, that's a good one. I think it was an alternative data project that I'll be telling you about, although there's some linkage issues as well. So with that, let's go ahead and jump in. Next slide. Okay, so as I said, I was working with the Consumer Price Index housing team, and this particular team occasionally needs to verify the BLS data, the Bureau of Labor Statistics, subsidy and unit level data. And so the project looked at matching techniques with the Housing and Urban Development, also known as HUD data, as a supplementary data source to do that checking. And the goal of the project was we took a year of data from both sources to see there was a current matching methodology to see if we could improve that. So there was a desire to get better matching outputs and to see if there was a whole other approach that we could use as well. Next slide. This quick shout out to the team. I was the lead data scientist on it, but there's many subject matter experts as well as product owners working with me on this as well. And so props to everyone listed on the screen. Next slide. Okay, I briefly kind of want to get us all on the same page, because one of the things that's really, well, terminology can be interesting. And if you go online and look up address matching, hey, what's address matching? Geocoding is like the first thing that pops up. And for this project, there was a clear distinction of what the team was looking for. So geocoding, you can think of that as, I have an address. Can you give me the approximate location of that address? Normally longitude, latitude, that sort of thing. What we needed for this project was to take two separate addresses and make sure and verify that it was the same exact physical location. So for example, apartment A of building 123 street, Main Street somewhere. And so that was the desired goal from this project, or what this team needed for the index. Next slide. Okay, just to kind of make sure we're all on the same page for addresses, the different components that went into it were, as I listed, like an apartment number was optional. Sometimes it was theirs. Sometimes they had it. Sometimes it was not. It was a home. Street address, city, state, zip code, all of that went together, and all of those needed to match so that we could verify that it was the exact same physical address. Next slide. I hope you guys can already see, like, it's getting complicated, right? There's already decisions that went into this. The current methodology that was used was rule-based. And so here you can think of the string matching rules, right? The case, the spacing, the punctuation, and I'll get a little bit more into that on a later slide. And the outcome for it was either it matched or it didn't. And so very binary in nature. And so we, for the project, we wanted to verify that the way that they were doing the matching was as good as possible, and we couldn't improve it, but also was there another way to do it? And we went a fuzzy matching route. And so that was a more probabilistic approach, a continuous kind of result. So how probable is the match of these two string addresses? Next slide. Very broad level view of kind of the flow of the project. We had the two different data sets, and that middle address filtering, of course, a lot happening there, pre-processing the data, trying to clean it up as much as possible, and match, right? Match the two so that we could make it work. We did different types of matching. So the exact address being the full address as we had it to match for a physical location. We also wanted to see if we relaxed that a bit, what might happen. So that's, if we didn't take into account an apartment number, how close could we get? Could we match a building for an exact match? And then the fuzzy matching, which is based purely on string edits and substitutions and all of those wonderful things to give us some sort of probability for that match. Next slide. Okay, some of the challenges, I briefly mentioned some of these already, but of course, across two different data sets, you're going to have different missing values. You're also going to have different types of ways of indicating those. So that was we actually had multiple null value indicators across the different types of the two data sets. There was decisions that had to be made about how to handle missing data. There was actually redundancy within the supplementary data. So we could, if missing, check another column, if you will. And so making decisions about that. There was many punctuation things, as you can imagine, with addresses, numbers, numbers, lots of numbers in there, and people write them many different ways. And also just punctuation, like commas and dashes, that mostly it was easy to handle. And then there were those wonderful exceptions that just made you want to pull your hair out. But decisions were made, it was good. One distinction between our challenge as well was that the BLS data was a much smaller data set. So we had thousands of addresses in that year of data. Whereas with HUD, the supplementary data, there were millions of rows of data. And so there was that kind of mismatch between the two, and figuring out how best to search, right? How best to try to match. Human error and variance. So depending on the part of the country you're in, we put quadrants in different spaces in an address. We write out the names differently with small little things that human text, right? That's just a component of it that really can be very fun, but also challenging. Another way that we thought about it was, do we want to look at it as one string or as different components within a string? And if so, how might we prioritize that? So decisions there, and then also looking at the outcome for the different types of matching. So a lot of different things to make decisions on in the project along the way. All right, next slide. An interesting component that was an amazing thing was the expectations that we had for the project. And so current literature, when looking at address matching, suggested that we should get a very high percentage match. And so we really wanted to improve what the existing match was putting out. And through the course of the project and looking at the exact matching and looking at a semi-exact, so building matching, and looking at the fuzzing matching, it wasn't producing the results that our expectation was. And so then at that point, it worked out best to step back and say, well, where did our expectations come from? Why do we think that we can get this? And it was current literature. And so then doing kind of an adjacent kind of literature search to say, okay, how is it different? What are we not doing? Or how might we improve the methodology that we have going on? And finding out that there were components that we didn't have access to. So something like the MAF master address file, we just didn't have access to that. That was one component that was used in some of the literature. Also different access to some PII to matching with, administrative kind of data. And then also the idea of one example being if it was considered deliverable by the post office, it was an exact match. And so that was not within the limitations or boundaries that the team needed to say, no, that's an exact apartment in an exact building for that physical location. So we found out that our expectations were slightly off. And so we were able to reset those and move forward with the project. So that was a really interesting pivot that happened within this project. Next slide. So the outcomes of that project were that we had a few minor suggestions to improve the current methodology, but nothing that improved it significantly. And then also knowing that in the way that exact address matching is defined for this team, we couldn't get a better fit with the supplementary data that we were using. All right, next slide. Yeah, thanks.
Passing it right to Missy. Thank you, Amy. And again, if you have questions, this is for the audience. If you have questions for any of the projects in particular, feel free to drop them in the chat as we go. I'm sure our speakers can answer them if they spot them, and it's a quickie. Otherwise, we'll get to them at the end. There's going to be kind of a lot of information at the front load, and then we'll have a more loose conversation afterwards. So with that, Missy, take it away.
Great. Thanks, Erin. Thanks, Amy. Let's go to the next slide. Before I jump into the diary autocoder, let me just quickly orient everyone on the call to the CE surveys. So for those of you who don't know, these surveys collect information on the complete range of consumers' expenditures, as well as income, some demographic characteristics, and this comes directly from the consumers. We have two surveys in CE, interview surveys conducted via a CAPI interview, and that focuses more on larger and recurring expenditures, while the second survey, the diary survey, is focused more on day-to-day and smaller expenditures. Today, we're going to be talking strictly about the diary survey. Our data is collected by field representatives from Census, and it's an important input to the Consumer Price Index, which most of you, I'm sure, know, measures price changes, that is, for a market basket of goods. And CE expenditure data is really what informs that market basket. The diary expenditures are recorded by the respondents themselves. This self-administered diary data needs to be digitized by our partners at Census. And while we do offer online diaries as an option, the majority of diaries are kept on paper. And we found that that continues to be preferred by respondents, interestingly. Those paper diaries must first have their entries, their whatever is recorded by the respondents, manually keyed in. Both online and paper require each expenditure to be classified into a standard classification system. We call them item codes. And this item code structure makes our data usable for downstream use cases, whether that's aggregating it in a way that the CPI needs or aggregating it for publication purposes or other uses. Next slide, please. Let's start with an illustrative example of a diary. So there are 4 main sections to a diary. They reflect clothing, food at home, meals outside the home, and all other expenditures. And what you'll see here is an example of one particular day of purchases from the clothing section. And we collect expenditure data, anything that occurs on any of the days within a 2-week period. So you would see one of these for each section for each day of the diary period. You can see that what we asked for was what was bought. And the respondent has the option to describe in their own words what it is that they bought, as well as, we're capturing what it costs, the age and gender for the clothing item, and the store. Now, as I mentioned a minute ago, all of this information would be keyed in by our partners at Census. And of course, yes, there's opportunity probably to improve that keying in approach through like OCR, other automation, but that's outside the scope of today's discussion. What we're going to focus on, and the purpose behind the CE's diary autocoder, is classifying each of these individual expenditures into common item code categories. Next slide, please. I think it's helpful to consider an example here. So what I'm showing here on the left-hand side is a way that we can aggregate clothing expenditures based on whatever was written by the respondent across all of the diaries that were collected for a specific reference month. And so here I've come up with just, a number of ways that someone might record the purchase of pants. And I'm sure this is nowhere near exhaustive of what someone might write. Now, these descriptions all ladder up to an item code for slacks. And I'll add here that the particular item code classification system that we use, it's one that's maintained internally by BLS, and it's used specifically for classifying what you can think of as like the lowest level consumer expenditure categories. Now, given this hypothetical example, I want you to imagine the decisioning that must go into selecting item codes, not just for slacks and however they're described, but for every item that gets recorded, and the myriad ways that an item could be described by a respondent across, I think it's nearly 1,000 possible item codes. So that's a lot. Let me contextualize that a little further with some numbers on the next slide. There are about 30,000, give or take, diary expenditures that are collected each month. And so that means that 30,000 items require an item classification. Now, our partners at Census, who field these surveys for us, do have a process to identify direct text string matches to the degree that they exist. And that does cut down on the volume of manual decisioning that needs to be made to classify expenditures. But all told, when you consider, because it's all kind of commingled in one workflow, the keying of entries, the item code decisioning, which actually involves multiple layers of processing and adjudication and review, all of this happens across approximately 8 weeks for each month of data. And that 8 weeks is in addition to the additional processing that happens at BLS, the validations, transformations, aggregations, et cetera, before we can pass it on downstream to our users. I also want to add that through an internal analysis on a sample of data, which went through its own multiple layers of individual review, we have estimated that about 11.8% of records are misclassified. And I want to be clear here. I'm not here to suggest that 11.8% is a good or bad result. It's a baseline for us to work against. But of course, you know, humans are human. We're going to make different choices under different circumstances. Sometimes words and phrases are ambiguous or have multiple meanings. Depending on where you are in your tenure, you might make different choices based on your familiarity with the item code structure. So there are any number of reasons why misclassifications can occur. But given sort of this backdrop, you know, we ask the question, because there's always and everywhere a need for more timely data, is there a way for us to speed up this process while achieving at least the same level of accuracy? Next slide, please. Of course, the answer is yes. That's why we're here today. There are 3 opportunities that we think an autocoder can solve. One, obviously reducing the processing time, as well as reducing the cost to maintain the systems and resourcing tasked with supporting the item coding, all while maintaining the same or hopefully even greater level of accuracy. Next slide, please. So let's get into what the autocoder does. It's actually a multi-step process that ranges in complexity. We kind of start simple and work our way into more complex approaches. So the diary section for recording expenditures that are meals outside the home, like restaurants, actually just the way that it's recorded contains enough information and our corresponding item code structure is simple enough that we can use a simple rules-based logic, and that's going to be sufficient. And I would say the lesson there is don't make things more complicated than they need to be. I'm going to get to a little more detail on the next slide, but before I get there, let me just quickly talk about the other 3 expenditure categories. We start with seeing if we can make direct text string matches between what the respondent wrote and what we maintain in kind of a dictionary of commonly used descriptions for each item code. Our partners at Census have developed that dictionary and have maintained it over time. With the launch of autocoder, we at BLS now continue to modify it and add to it. And all told, about 50% of records can actually be direct matched. If we can't make a direct match, then we move on to machine learning, which is a predictive approach to assigning an item code. And then we do some additional checks against those machine learning predictions. First, there's a fuzzy match between the diary entry and its predicted item code description. And we also check to see if there are multiple items recorded in an entry. And sometimes respondents do that, right? They'll write everything they bought in one line, like shirts and pants and backpack might get recorded as quote unquote one expenditure. In those cases, we'll assign what's known as a combo item code to those items. Let me jump into a little bit more detail on the next slide. Okay, let me talk about direct match. So direct match itself is kind of an involved multi-step process too. We're attempting to match what the respondent wrote against a dictionary of commonly used words and phrases that ladder up to an item code. But that dictionary is not exhaustive. And we need to do some processing on what we call the incoming phrase. And this just means things like removing extra punctuation, removing colors from clothing expenditures, like red shoes becomes shoes, removing major store names or brand names from the expenditure description, which I'll add means we also need to maintain a file of brand names as a reference. And we also have a process that compares text strings if we change the order of the phrase. And I'll give you an example there. So one person might write something like Halloween costume, and someone else might write costume hyphen Halloween. And so we want to check, right, both of those sequences to see if we can make a direct match. And the more we can get to a direct match, that means the lower the burden on the less accurate predictive component of autocoder, and what will also mean the less human review of results that we need to do. Next is machine learning. Here, a classification algorithm is tasked with assigning or classifying expenditures into these predefined categories, these item codes, using pre-categorize data to learn what that classification process ought to be. And we evaluated a number of approaches like logistic regression, XGBoost, et cetera. We settled on random forest. For those of you who are practitioners, it's an ensemble learning method. We thought that it gave us a good balance between model complexity, which includes things like how long does it take to run, how big is it, and accuracy. And I'll say that each machine learning prediction comes with a probability, and that probability kind of reflects the level of confidence in a prediction. And again, for the practitioners, it's just the proportion of trees and that ensemble that result in the same item code prediction. What's important about that probability calculation, though, is that we use it to create thresholds and flag records for additional manual review. Now, manual review, it could be as high as 20% of records. It's an important component of the process because no model will predict outcomes with a high degree of confidence for every observation. There's just too much variability, right? And so adding a layer of human review means that we're able to increase the accuracy and achieve the same level of accuracy as the manual coding approach, the old way. Similarity ratio, again, I mentioned this was a fuzzy matching approach. We only do it for the output of the machine learning predictions as an extra step of validation. And we do this regardless of the level of confidence from machine learning. I put the formula here. We experimented with different cutoffs by manually looking through data, and we kind of settled on a value of 0.87 as the cutoff. And I'll explain kind of why that works for us. A 4-letter word can have one typo or one letter differential and still meet the threshold. So a good example here is sock and socks, which are the same thing when you're talking about clothing. But in contrast, words like shorts and shirts each have 6 letters, 1 character differential, clearly 2 different items. They'd have a similarity ratio of just 0.83. And so if that threshold is not met, it gets kicked out for human review. Let me just summarize by talking about results. We used a sample of data that was held out from all of model development, and we did some independent item code determination and adjudication across 3 BLS staff. We call it our gold standard data. Think of this as a source of truth. And we compare census accuracy with autocoders inclusive of manual review of flag records accuracy, and found that we were different from each other by around 1% on average, and that was well within the margin of error given the sample size of the gold standard data. And so we were satisfied with those results. Of course, in the future we're always going to try to find ways to improve accuracy, but we're very happy with that result. We also, and maybe equally as importantly here, we reduced the amount of time to assign item codes by an estimated 73%. And that includes the time that is spent by our staff, reviewing, validating, possibly correcting any record that gets flagged. We just launched autocoder into production in January of this year. So we're still really in the early days of having this capability operationalized. And I know during the discussion, we'll get to talk about like some of the learnings from that process. And so I think that's it for me. I'm going to hand it over to Danny now.
Awesome. Thanks, Melissa. So yeah, howdy everyone. My name is Danny Todd. I'm a data scientist for the Office of Compensation and Working Conditions here at BLS. I'm currently the product owner of the Survey of Occupational Injuries and Illnesses, also known as the SOI autocoder. Next slide, please. So just for those of you who are not aware of the SOI, it is an establishment survey, and on average, we get over 200,000 injuries reported each year via this survey. Information from this survey includes things like job title, source of injury, the part that was injured, etc. So we're essentially trying to get all of the injuries that happen across the US in a given year and get as much information regarding what happened, what caused them, etc., as possible. Now, to better understand the data, as many of the other survey programs do at BLS, we actually have to assign codes to all of these free text narratives. That way we can downstream aggregate all of the information about them. So if someone says, oh, I fell and hurt my arm, and then another person says, oh, I tripped and hurt my arm, we want to be able to realize that arm is the same part being injured in both cases, and there is a similarity between them. And so to do this, we categorize these fields by the Occupational Injury and Illness Classification System, or OICS, as well as the Standard Occupation Classification System, or SOC codes. Next slide, please. So here we have a soy case coding example. Every day throughout the year, we get a bunch of narratives in that contain the information such as the job title, what the employee was doing before the incident, what happened, etc. And then Aaron, if you want to just like click, ooh, magic. And then just like the autocoder, codes magically get assigned. And then these are downstream used to be able to aggregate this information. So as we can see in the example here, we would have an occupation code describing the job of the injured worker, as well as the nature, part, event, source, and in many cases, secondary source codes, which are all assigned to each individual soy case submitted. So historically, this was actually done. Each case narrative was read and coded by hand, which was obviously extremely time consuming and somewhat prone to errors. Next slide, please. So how did the soy autocoder come about? At least internally, we refer to it as the CAC for computer assisted coding. And initially the CAC grew out of a number of things more than 12 years ago. Before its inception, like I was talking about, all codes were assigned manually. Considering the fact that we collect hundreds of thousands of codes each year, or cases each year, we required many hours and quite a bit of manpower to actually manually code each of these cases. More importantly, early research on soy undercount indicated that manual coding was highly inconsistent. Two experts coding the exact same narratives had only approximately 70% agreement between them, so they would differ very frequently when coding these cases. Therefore, we wanted to try and improve this process. We needed a process that was more efficient, as well as allowed consistent coding across staff and regions. So that way, if we get two slightly differently worded cases, they will wind up getting the same codes. So that way, when someone does injure their arm in two separate cases, even though they're worded differently, we can still result at the same codes and understand that there are similarities between them. And so all of this raised the question, can a computer help us to do this? Next slide, please. So starting back in 2012, BLS, specifically Alex Measure, began investigating machine learning for coding cases. And by 2014, we actually had our first production models being used to help code cases. Like I said, this started with a logistic regression model and evolved downstream to use a long short-term memory, or LSTM, model a few years later. Subsequently, we transitioned into the current iteration of the autocoder, which uses a large language model, also known as transformer architecture, which was first implemented by Alex and the team in calendar year 21. Now, I'm sure most of you have heard of ChatGPT by now, and coincidentally, what GPT stands for is Generative Pre-trained Transformer. That's the same thing that we're using. So the micro architecture and the mechanism behind how a lot of these things work is the same in many of the transformer architectures. Now, this is the most popular and efficient approach today that takes neural network models essentially trained by big tech companies like Facebook and Google and applies a process called transfer learning where they generate the base weights for these models. And then we pull in that model and essentially fine tune it for our specific use case. So the way I like to think about it is they give it a overview of, say, the English language. And then when we go in, we say, yeah, you might know all of the English language, but we really only care about what applies to the soy. So you can forget all of the other stuff and really just learn how to predict soy cases well. And ultimately, this allows us to get a model that is fine-tuned to predict cases from the soy. So transformers are ultimately great given that minor inconsistencies such as like typos and whatnot don't necessarily impact the predictions that the model makes nearly as much as, like, say, the LSTM or logistic regression models. So they are somewhat more resilient and robust in that sense, and allows us to subsequently pass that on to the data that we're collecting and labeling. Next slide, please. All right. So here we just have an overview of the historical breakdown of the percent of codes automatically assigned by the CAC annually. In 2014, we started using our autocoder and initially just to automatically code occupation codes. It worked well. So in 2015, we expanded, now coding nature and part codes as well. In 2016, we expanded even further to code things like event and source. And at that point in time, we were auto coding about 50% of all codes going into the soy. In 2017, we actually took another jump and we surpassed 2/3 of all soy cases. By this time, we were actually at the point of diminishing returns where we couldn't increase the amount that we were auto coding reliably without reducing the coding quality, specifically on rare codes. So some things are very common to happen, and then there are other extremely rare events. Like you can imagine tripping and falling is a very common injury that happens in the workplace, whereas some obscure, like a tree falling out of the sky might not be that common. I'm sorry, that might have been a poor example, but for rare codes, it's very difficult when you don't have a lot of training examples. So our autocoder learns from previously coded data. It is a form of supervised learning. And so it's unfortunately incapable of predicting things that we haven't taught it to do. Over time, it's learned and has progressively gotten more and more competent at predicting codes and has learned to perform better and better through the years, with our transition to neural networks and subsequently language models. In 2020, there was a bit of a decrease, as you can see, for the amount of codes that we automatically assigned. This was ultimately due to new information being introduced into the soy, which was not previously available in our training data, with that information being COVID. Prior to 2020, we had not had any COVID cases in the soy, so we couldn't teach the model to classify these. And as such, we had to put a bunch of safeguards in place to make sure the model, when it sees a COVID case, it wasn't just going to try and classify them, because we know it would get it wrong. So since then, the CAC has ultimately gotten COVID cases added to its training data set, and we've returned to the previous levels of coding, and has even increased to ultimately code a large portion of soy cases annually. Next slide, please. Now, two things I do just want to bring up, because I feel like it's always important to bring them up. First off, with our model, this is, again, a production model. It is a production system. All of the predictions that the soy autocoder makes are reviewed by a human staff prior to being used. So ultimately, at the end of the day, what we're trying to do is save people time for those very common cases that are relatively easy to code and allow them to spend more of their time focusing on those rare cases that might take a bit more thought and actual logic going into it than potentially a language model can handle accurately at this time. So again, a human is always in the loop in our scenario. Additionally, we use a subject matter expert coded set of data each year prior to deployment just to evaluate our model and make sure that we are performing adequately against a ground truth data set and that we aren't just spitting out garbage codes, if you will, that don't necessarily apply to anything. And yeah, that's really all the background I got. I guess we'll kick it back to Aaron.
Thanks, Danny. Thanks, Missy and Amy. That was great. So really all of that preamble is kind of table setting, little context, okay, so you can appreciate the expertise that we have in the room, but I'll just take a minute kind of to further highlight the fact that these projects are at very different stages, which comes, each with its own challenges, but together, and why we thought they sort of fit nicely in this panel, we have a pretty good picture of what we're calling the full development cycle of an NLP model as a product. And I'm putting air quotes around product, although it's a real thing, I promise. Actually, yeah, and I'll take a minute to define this because it seems worthwhile. We keep saying the word product or productionize. That actually can kind of have different images probably to different parts of the audience here, but I'll just say kind of what we mean really. It's a broad thing, but what's a product? It's any tool, any service or set of capabilities that have been designed to serve the needs of a defined user. Or maybe I could phrase it as like the defined needs of a very specific user, right? Because scoping is a big part of a sort of successful product development cycle. So we know about data as a product is statistical agencies, like we often put out data, that's a product. But if we're talking about a model, right, for example, an NLP model, and we want to deploy that model into production, we're sort of talking about a holistic, ideally very robust approach to scale and automate the model in a way that integrates with other systems, right? So we've heard about that with the C autocoder and the soy autocoder. There's other systems here. And it needs to solve also for the interface of users of those systems with the model output, right? So there's a lot of apparatus that comes around the model itself. It's more than just building the model, which is kind of growing the expertise, growing outside of the initial scope of if you trained as a data scientist, right? The first thing you learn, right, is about this model development cycle where you build a model, you evaluate it, you go back, you make some different decisions, evaluate whatever, you go in a loop with your validation data. Eventually you have something worth sharing and you're ready to kick it over, let's say, to some stakeholders. Around that sort of model building phase, we have these pre and post, let's say, communication requirements, right? Initially, you have to understand your opportunity, right? You have to have those conversations with your stakeholders about requirements, about expectations. We heard about expectations a lot. Thank you, Amy. We'll come back to that. This is also, when you access and you explore the data. And then after you've built the model, let's say you've got something that you think is doing pretty well, you have to communicate that back with your stakeholders, right? And those conversations might move you back right into building a model. So there's a bit of a loop here, but we're also talking about what you do after that, right? If you're successful with building and communicating your model, right, which is not an insignificant thing on its own, you get buy-in, let's say, from your organization. All of this stuff has to come later. You have to deploy the model into production. You have to monitor model performance, periodically update the model, right? Which also might kick you back into those initial steps of understanding your data again. I think we'll talk a little bit about data drift as well. And you might need to revisit your expectations and the requirements with your stakeholders and update those as things change, right? Because we know we train a model with, holdout data, but the world changes over time. And sometimes you have to kind of rethink what you can really get out of that model. Right. So the point is really these projects are not one-time efforts, right? We're not just running an analysis, we're building something. I guess that's kind of in some ways the big difference between being an analyst and a data scientist. Like we're building a thing. And we have a lot of collaborators, a lot of stakeholders, and we have to think about the end user of the product or the tool. right? So that's a lot more than the building model. So we just heard about the example projects from our panelists, and I don't need to probably say it, but right, Amy was talking about something in the research phase, sort of the top of this little graph, building the model, communicating, understanding the opportunity, and a lot of that cycle. Missy presented the CE autocoder, which is new, right? It's an initial deployment, and she already knows that I'm going to ask to unpack that deploy model box, which is egregiously small. I know it's very complicated. And then Danny spoke about the soy autocoder, right? A mature model. So we're 12 years old, and it's being monitored and has been updated. You know, so there's a lot there that we can learn. I am now going to transition into Q&A, and again, as questions come up in your mind, audience, please put them in the chat. I'm going to keep an eye on that. I'm going to stop sharing my screen. Hopefully that looks good. I can see the chat. I can see the panelists' faces, and I'm going to start asking questions. Okay. I'm going to start with Amy, if you don't mind. The product introduction, right, covered the motivation, right, the why do this. But was there a point, and you sort of spoke about this, you realized that it wasn't perhaps the right tool for the job, or I won't say it that way, but you kind of, when you realized that you weren't seeing the same outcomes that you were expecting from the literature review, how did you manage those conversations, and what are the lessons there about maybe time boxing, pivoting quickly? Anything you can elaborate there about that?
Absolutely. It was an interesting project. I think that very rarely is there such a great example of like, oh, let's pivot or step back is maybe a better way of thinking of that. From the beginning of this was not my first natural NLP project, and so I was familiar with the current methodology that they had been using, and felt really confident in that. And so I didn't have doubts about either the rule-based approach or the probabilistic approach. I'm familiar with both. And we explored some, do we want to try neural net and things like that? Like, do we want to extend even farther? I mean, it was like, well, let's see how the fuzzy matching goes, because that will indicate for us, like, if there is more to be found in outside of that rule-based kind of approach, right? Let's get away from that. And that just wasn't the case. We didn't see that, oh, yes, there's this beautiful, we're missing it. We're missing everything, and it's just right there. And so that kind of, let's see, it was conversations, right? Talking through the results and trying to put it in the framework that the housing team, that it resonated with them, that it made sense with what their subject matter expertise was. That sort of kind of elucidated that, okay, it's the expectations that maybe we need to think about, or why should it be so good? Why should we get such a high matching amount, and where does that come from? And so I'll go back, I'll say communication a lot of times today, I think, during this session or panel. But it's so easy to just make assumptions that we're all on the same page, that we all understand what, I think we've already talked about what model means, what production means, what all of those things mean. And so that was probably for this project, just kind of figuring out how to get on the same page about that, and then exploring, well, what is there, right? What is in the literature, and then how can we use that? And so that as soon as we got on the same page, I think that it was a much smoother kind of, oh, okay, well, let's answer this question. Let's answer this question. How far can we go? And so, yeah, definitely a little bit of shifting, but more on that expectation side.
Just following up on that, the kind of, I'm going to say post-mortem, but that's a term I used to use a lot with product managers. But when you kind of sat down and thought, like, what is it that we're missing that the literature has that we don't have? Like, that seems like that's a good conversation that we should probably all be having when we're launching new projects. Like, we know the problem, that we don't see the failures in research write-ups. We only see the successes for the most part, and that can kind of imply things work better than they do. And often it doesn't work that great, but nobody's reporting on, like, oh, I tried it for this. Actually, we have a question that I'm going to come back to which is like, do we have any, themes for when a model doesn't really work in practice? And the answer is, I don't think we have like a good literature to lean on of like, okay, these are the use cases that have not worked. We often see the successes, but not the fails, right? But I'm thinking like, those conversations that you had with stakeholders where you sort of said, this is what our expectations were from the literature, but look at all the stuff that they have that we do not have. Would you recommend having those conversations like as soon as possible, like time boxing maybe and going back with like early results?
I'll say yes is the short answer, but let me kind of let me say more. First, I definitely don't like the postmortem, but a retrospective. I'm a fan of the agile process, and so I'm probably going to mention that as well in this. In that's sort of the mechanism that I like to use to make sure that there's no judgment. There's no, this is just what we tried and it didn't work. That's just where we're at, and how can we go from there? And I really like the agile process because in the framework, because it just allows for that. It's let's iterate, let's pivot, how can we move forward in the quickest way possible to an amount till we get to, the returns aren't quite right. Like we don't need to go any farther. And so I would say that I would have liked to have done it sooner, but this was a learning process of understanding how to frame the questions, how to understand what it was that I needed to look into, or we needed to talk about, or make decisions on. Yeah.
Awesome. Thank you, Amy. And Missy, I see you're active in the chat. Great. But I'm going to pivot to you now because you've got a lot, I think, that you can explain for us in that deploy section. Let's just unpack, what does it actually take to get a model, a proven model, let's say, from sort of this experimental phase and into production?
I have a lot to say here. Yeah, so let's start with just sort of like the initial phases, which predate me, but kind of like the beta or the proof of concept version of our autocoder was, initially developed a few years ago. It was built on a laptop. There are many limitations with that approach because it's not really a sustainable operational framework. When you're using, like, say, 2 years of historical data to train the model, to teach it how to learn, that can be like hundreds of thousands of records, and the model's trying to learn how to classify across hundreds of item code categories. That's too much for a laptop, right? So you need you need a little more horsepower. You need a bigger space in order to make this feasible. Now our autocoder, all of it is built in Python. The machine learning component, the models were built and will be rebuilt, retrained on an existing Linux server that it's dedicated to development activities in the CE program. And then it's run in production on a different Linux production server against incoming data. And then that output, gets loaded into our Oracle database, and other things happen. Now, to get from like that proof of concept to production, of course, was non-trivial. And I think I'm kind of thinking about this in probably 3 main ways that are like what was needed and what we learned or had to figure out along the way. So I'll kind of like commingle those things. So first, just because you have access to a server doesn't mean that you have free reign to build big and complicated models. Seems obvious, but it's true. An important consideration is the model files themselves. And that's what's kind of read in when autocoders run in production, and it kind of has the instructions for how to make a prediction for each record, like the food and beverage and other expenditure categories are huge. They're our largest expenditure types, both in terms of just the number of records, the number of possible item codes. And so, you can build really big, complicated models that will get you, pretty good accuracy, but, the model size can be quite large, and you don't know if your server can handle that. And, let me just cut to the chase here. As we were set to launch, we discovered that our production server in its current state couldn't handle, at least one of our models. It was just too big. And so, we had to spend another several weeks tweaking the model, doing some different sort of hyperparameter tuning, trimming some trees, just making the model smaller, but also at the same time, right, we're trying to evaluate accuracy. So making sure that we're not creating material loss of accuracy. And the other thing to note here too is that we run autocoder on servers that house other production activities. So it's not the only thing going on that server. So we've had to set it up so that it's using, I think, no more than 1/4 of the available cores. And depending on your data, like that can make your run times longer. And what does that mean for your timelines for production? And like, when do you need to run this thing? Does it need to be run in the evenings? Like, we actually, it turns out, haven't faced that issue. We can run a full quarter of autocoder data in just over an hour during the day. So that's great for us. But we had to figure that out, right, as we went along. The second piece I would say is with regard specifically to deployment planning. And I mean, my advice here again seems obvious, but true, leave more than enough time and sufficient resourcing for deployment, because you're undoubtedly going to encounter unexpected issues. We in CE, like maybe many folks on this call, have historically been a SaaS shop. And while CE does happen to be going through some systems modernization that utilizes Python, implementing machine learning in perhaps new or unfamiliar language, creates integration challenges, and a lot of learning that needs to happen if you don't have that sort of built-in expertise among your technology support teams. And this was the first time that CE integrated machine learning into its production systems. And I think it's important to be cognizant that it may be your technology team's first exposure to machine learning, and they may not have all the answers that you want them to have, when you're asking implementation questions. And so it's going to require kind of cooperating and learning together, probably a little bit of trial and error, just like the server situation and the model size situation that we encountered. But it's just, something you have to go through. And, let me be clear, like, technology team, they have a lot of responsibilities, right? There's all sorts of configuration management, the server, the Python versioning, GitLab, design documentation, issue tracking, all that stuff. They need to know how the thing works. They need to know how the code works in order to configure the environment properly. And so data scientists, program office, technologies all need to work together to figure out and understand what it's going to take to get it to deploy. And I would say too, they were really great at working with our data scientists to implement software development best practices, things like modularized code and unit testing and things like that. So that was great. And then I think the last piece I would touch on here that is something we're still kind of figuring out is maintenance. And this involves both like troubleshooting in production, what happens when things go wrong, and then planning for the future, right? We in CE are pretty fortunate that there's enough time between kind of when the data gets received from census and when we need to start processing it, that, when we run autocoder, which happens before we start our processing, if something goes wrong, or maybe we have to upgrade Python, we need to do some testing or whatever, we have enough time to kind of sort that out, but not everybody does. And so making sure that when you're kind of plugging in a new process or capability, you've got the resources and sort of the calendarization kind of really thought through about how that's going to work, especially and when something goes wrong. And then, thinking about the future, depending on where this goes, it involves questions like, what are your server needs? What are the staff skills required? What does ownership mean? Like, what does ongoing ownership and maintenance look like? Who is doing what? And what are those roles and responsibilities of like data scientists versus the technology team versus the program office? What are those infrastructure and development needs for more advanced models like Danny's journey? I'm sure we'll hear more about that. You know, if you're using more data, more complex processing needs, what are you going to need to do as a program to support that? This probably won't be the first machine learning model, or sorry, this won't be the last machine learning model that we implement in production. So assuming this is the wave of the future, kind of like what is our like operational model and ownership model need to look like, knowing that we're probably going to do more of this, not less, in the future. So I don't have all the answers to all these questions, but these are things that we're thinking about.
That's awesome. Plenty of stuff to think about there. Just I don't know if the audience is also wondering, but like, let's say order of magnitude time between proven model and out the door in production. Talking, how long was that for the CE autocoder?
I think 2 years.
2 years.
When we started building this version of the model to when we actually ran it for the first time on production data, it was just about exactly 2 years.
I think that's good context. I think especially if you're in that sort of model build bubble, it's like, oh, you're moving so fast and you're getting great results. And then like, it can feel like walking through molasses to actually get it into use. But don't be discouraged. And actually, speaking of production, Danny, what have been, I should work on my transitions for the next time I do one of these. What have been the biggest challenges that you faced when it comes to sort of monitoring and maintaining a model, right? You're several years past what we just heard about with the CE autocoder, but knowing that that's the big challenge that they're looking forward to, or looking at and down the barrel at, you know, what are lessons that you can sort of pass along?
Yeah. So I guess first thing that I'll say that I think almost every person who's ever taught me coding will be super happy to hear is number one takeaway is documentation is key. Like, yes, we have researched and developed this process. We do all these things, making sure everyone that has a stake in the outcome of this is aware of what's going on. Your code base is readable, understandable by other people. It's not siloed with just like one person and treated like a black box. That's super important. As well as understanding the whole process. Like, okay, every year we need to get new training data in because new training data comes in from the SOIs. So, all right, we need to update our training data. Then we also need to like train a model. And what about like thresholds? Do we want to set probability thresholds? Are there certain things that maybe we should look out for? How are we getting the model out to the server? Are we doing this with a CI pipeline? How does the CI pipeline work? And so you start going down all of these various paths. And I would say the biggest challenge to maintaining is just keeping an accurate list of, hey, this simple code package that used to be just a model has now evolved into many, many code packages that touch such a wide variety of things, from like, we have dashboards that do monitoring to see like what humans are changing. Is there a systemic issue with the model going on? How are we performing like what we expected to see versus what we're actually seeing? Are there major differences there? And it starts to really branch out, and having a clear picture of exactly what's going on, having all of that defined in centralized locations for everyone else on the, not only the team, but just the entire process to be able to access and understand easily. I would say that that's the biggest challenge. Obviously, when you go down each of those rabbit holes, there's like tons of other minutia and challenges and whatnot. Like even just for example, like AI is still very new to government. How do we walk through that path of, is like we want to make sure we're following all the rules and whatnot? Are we using safe open source packages? Is everything authorized in terms of like security and whatnot? And you start going down those lines of, do we have our environments documented? And I would just say, yeah, you go down rabbit holes extremely quickly, but it's exceedingly important, especially for a production model, to go down those rabbit holes and make sure that the whole picture is taken care of. Your T's are crossed, your I's are dotted. You have your unit tests in place. Everything is set up and working as people think it is. Yeah.
I have so many follow-up questions, but I might just take a moment to sort of say documentation +1, just logistically, where are you maintaining your documentation actually for all of these projects?
So we have basically two places. Obviously, the code itself, GitLab is our favorite go-to. No better place to keep documentation than with the code that's actually running. And then in our documentation, we generally tend to say like, hey, this code runs on this server and it does this process. So that way anyone who does come into our code bases can see like, okay, this is kind of the big picture. And then in terms of other documentation, we also have like a SharePoint site, which doesn't necessarily go into as much technical detail of what we're doing, but it does give more of a high level overview of like, this is our process, start to finish sort of idea. And again, I should probably also harp on the fact that I say it like, oh yeah, you do it and it's done. It's a constantly evolving beast of like, we're always updating our documentation to account for things changing, systems changing. You upgrade like all of your software versions, you change how a model works a little bit, like everything downstream needs to be updated as well. And so for right now, that is the current system that we have in place. Will it be in a year, 5 years, 10 years? I cannot necessarily say, because these things do like to change all the time. But yeah, that's what we got currently.
I mean, I think it's a kind of under-recognized burden that can get kind of left until the end. And there's so much that we could all be doing better about documentation. But it sounds like you're kind of thinking already about two paths of documentation, right? One for the technical users, which is mostly in GitLab. And then separately, you have maybe a more accessible set of documents that are in your SharePoint. And I'm kind of wondering if anybody else is taking a similar path. Maybe CE or, yeah.
Yeah.
Jump on. Oh, wait, you got it? Okay. Is that it, Miss? I got more to say. More to say from the research side. Definitely that two paths. So code loves GitLab, GitLab loves code. But for the different teams, so the housing team was one of the teams I worked with, but I've worked with a lot of different teams in OPLC, and each team kind of has their own space that they usually like their documentation in. And so, but it's yes, there's not enough can be said about documentation and how important it is, especially in like the research projects, because often it keeps you on a path, right? And then once if you're meeting in an update or a demo, a sprint, and it can bring everybody, okay, this is where we're at on the path, right? Here's the documentation. And then it's also that vehicle that says, this is what we've tried. Do we want to keep going down this path, or do we want to shift, right? Maybe a small pivot, maybe a big pivot. And it's just, yeah, I would say I swear by it in pretty much all of my projects at this point. The documentation just makes it easier for everyone. And then having it accessible, of course, to anyone after the meeting as well.
I don't know, Missy, do you have anything to add on what lessons from documentation? No. Since we're on it also, we're kind of thinking about documentation for different kind of categories of collaborators, I'll say, your sort of technical and your non-technical, or not even, that's not even probably a fair way to put it, but let's say your subject matter experts, non-coder collaborators. And then we also have, the technology teams, or maybe other data scientists. There's sort of different modes of collaboration. I'm just wondering if you guys have lessons in general about working with different stakeholders and sort of successes, examples of successes. Maybe Missy, you want to start?
Yeah, sure. Yeah, I think it's really important for everybody, whether they're leadership, they're directly involved, they're peripherally involved, to kind of understand not just the goals of what we're trying to do, and not even just like the high level, how does this thing achieve those goals or how does it work, but more of the what's in it for me, or what am I going to be expected to do to support this thing. And I would say that a lot of my job as a product owner is just explaining what's happening or what's going to happen, in addition to sort of how autocoder mechanically works. And I think to do that is just, communicating plans, getting buy-in early and often, especially with technologies, because sometimes they're sort of tactically brought in later in the process during deployment. But I would say too, like, it was just as important to make sure that we were talking to the program office staff, the staff who were going to be responsible for doing the manual review part, because some of them were not, and probably still aren't, very familiar with our diary item code structure. We're asking them to take on new tasks that were new to them, and the topic was, somewhat unfamiliar. So those are some like challenges and tips, I think, that come from our side.
And Danny or Amy, do you want to add any successes examples? Otherwise we can scoot along. We're actually chewing up these luxurious 90 minutes pretty quickly. I will also remind the audience you are very welcome to raise your hand, come off mute to ask a question. Otherwise you can drop it in the chat. But while we have, I think we're at an end on 2:30. So in the last 15 minutes, please do come in with some questions. You'll get precedence, I promise. I'll stop yapping. But I do want to call attention to a question earlier from Haley about, actually Missy already answered from the sort of CE side, about themes surrounding examples when, let's say, machine learning models or transformer-based models fail for autocoding. And I actually want to kind of expand on that, and I'm going to pick on Danny to talk a bit about model drift and anything sort of you can talk about recent work that you've done with monitoring and updating. I'll say monitoring first and then updating a model and what you found with the soy autocoder.
Yeah, for sure. So I guess I should start first by just kind of reiterating, model drift is definitely a real, like, prevalent thing that needs to be addressed within machine learning. The way that the soy autocoder somewhat tackles that and makes it so we don't necessarily have to have that as such of a high concern to us is specifically just by having humans in the loop. In theory, if our model were just assigning gibberish for every single case, a human's still going to review every single one of these cases and hopefully pick up on the fact that we were assigning gibberish. So that does allow us to kind of keep that out of our mind to a large extent. However, each year, to also combat model drift, we are getting new data. So we are retraining the model. If new trends are happening in the soy, if new data is being introduced, in the case of like COVID all of a sudden happening, and now we have a ton of this brand new type of code being introduced, we do introduce that to our training data. And this is like an iterative process every year where we are pulling in the newest data, making sure to train the model on it, fine-tuning on the most recent years of data, because we tend to feel that that is the most relevant to what next year likely will have. And then I guess I should also probably talk about in terms of monitoring our model to make sure it hasn't drifted too much. We do have several dashboards, like reporting tickets, that if people are seeing like, oh, the soy autocoder is always coding X, Y, or Z wrong, we want them to submit help tickets and let us know. That way we can go back and say, oh, all right, is this like a statistic anomaly? Like, is this just a one-off thing? Or is this happening systemically? Maybe there's something in our training data. Is something in our training data wrong where we do need to address this, retrain a model, redeploy it, that sort of thing. And then just having like dashboards and whatnot, which keep track of, okay, here's what we've been predicting, and then here's what people have basically been disagreeing with us at. So it does give us some insights into, hey, these are weak areas where your model might not be performing adequately. But again, I would say all of that is held up strictly by the crutch of we always have humans in the loop, and it does allow us to take a lot of approaches to these sorts of topics that I know other people without humans in the loop necessarily might have to work around or approach differently.
Actually, it's interesting. I noticed when you guys are going through your sort of intros, there's a threshold for the CE autocoder to get flagged for human review. Is that right? But it's 100% of the soy autocoder output is reviewed in effect.
Yeah, so we also have thresholds as well. So everything above the threshold will get shown to humans who then have to review it. If it's below our threshold, we don't even show it to humans for review. We're just like, yeah, you need to assign that fully manually. We don't want to potentially assign like a really bad code, which could then possibly influence your decision, if you will. Yeah.
That's like a different way of putting it. Like you have to be good enough to be even like recommended to a human reviewer. Interesting.
Yes.
We have a question come in about the retraining. So you guys are both, I think, thinking annual retrains, just like it's a regular schedule.
Yeah.
How much? The CE autocoder is still new, so you haven't probably experienced this yet. Although I don't know, perhaps that's wrong. But for the soy autocoder, can you talk a little bit more about the retraining process? Are you really going back to basics and sort of rethinking everything, the structure, everything? I mean, we saw in your timeline how you actually changed models a few times. What, three times? You're on your fourth type of model now. But what else, right? Like, what else are you doing when you're doing your retraining annual?
So when we are doing the retraining, at least for the past 2 to 3 years, the way that you can really think about it is we have like a core model that then feeds into 6 separate classification models. So all of the text comes in through the core model and then goes out through all of the classification models. We do essentially retrain, I say, from scratch each year, in the sense that all of the classification models do start at like 0. We are reinitializing them every single time. But there is the core model, if you will, where we're using transfer learning, which we don't, I mean, we're not necessarily reinitializing that from 0. We are taking the weights and still doing transfer learning, but what its baseline was when we got it off of the internet, essentially, we start from that point every single year. In terms of over the years, the way I like to think about it is it doesn't necessarily matter the model. All that you really need to think about is like inputs and outputs. So long as the input to a logistic regression model is the same and the output is the same, in theory, you could put any type of model in that shoes, assuming that the inputs are the same and the outputs are the same. You can, and the performance is adequate, etc. But in terms of retraining, yeah, we are generally approaching it from keeping the same architecture that permitting all sorts of other things like processing speed, hardware capabilities, and whatnot. And I mean, if it isn't broken, don't fix it, I guess, is sort of been somewhat our motto of, hey, we have a good language model that's performing adequately. Could we use a different core model? Absolutely. Are we interested in it? Yeah, let's try and get more hardware. That way we can train on it and do those sort of things. But for the time being, yeah, it's been very just let's start from ground zero and retrain every year.
Are you thinking about, so sort of mid to long term, are you thinking about shifting off of, I don't know, did you mention what your actual core language model is into a different off the shelf sort of pre-trained model, or a different approach at all in the near future?
Yes. So I think as of this point, our core model is the Distill Roberta base model for any of the technical people wondering. And I think going forward, I don't think there's any real preference of like, oh, we want to use this type of model or that type of model. I think again, as long as it does, like, hey, it takes the same inputs, it works in this, like we have a list of system requirements that we need to meet. As long as it meets those and meets our performance standards, it's necessarily like, hey, if we can find something that can perform better, if all of a sudden like transformers came out and were created, we want to use those because they showed promise. All right, let's investigate them. And sure enough, they do outperform like LSTM models. So let's use those. And now if tomorrow a brand new type of model came out that we're capable of using and can perform well, by all means, yeah, as long as it's safe and ethical and all of those things, if it can outperform the current implementation, then let's use it.
What about the CE autocoder? Are there sort of plans midterm or even long-term to kind of reevaluate the model structure itself, or are you guys still in the phase of just getting it into production and used?
Yeah, I think it's too new. We're certainly not going to not do research in that space. It hasn't formally been thought about yet, but we do have kind of a dedicated data science resource. But I guess sort of pending his, availability and bandwidth and the program's needs, like I think my answer is it depends. For us, what we'll do is we'll continue to retrain every year as needed. We will need to like rebuild the models because we do periodically change our item code structure. And if it's significant enough, then you kind of need to like start from scratch. So when and if that happens again, maybe in 2025, that's something that we'll do, but we'll probably use, I'm guessing we'll probably use very similar approaches to what we're doing today.
It's interesting. I sort of wanted to highlight that because it's not represented in our little diagram, but the extra burden of your data science resources, right? It's not just maintaining the model or keeping an eye on the things that are monitoring output. It's also all of the extra research time, right? That needs to be sort of accounted for. Like if someone's going to be the owner of one of these products, you can't just be an expert at, frozen in time 2 years ago when you had your last success. You kind of always have to be looking for the new approaches that are coming out. We have 2 minutes. Oh, go, please.
It also gets to your organizational model too, and how you utilize your data scientists, which is, I think, really different for where Danny is versus how OPLC works. And that kind of gets back to what I was saying around roles and responsibilities and things of that nature.
I wanted to add something. I don't have a model to retrain, but I do have research projects. And one of the challenges, and if anyone has like the solution, that'd be great, but I don't think it exists, is feedback, right? We don't have, like, we can see how successful a project is, but in terms of communication, documentation, working with stakeholders and things like that, getting that kind of feedback, anytime we get it and it's helpful, we incorporate it, and it definitely has made different research projects smoother and working in different ways. But it's a challenge to figure out what to ask, when to ask it, how to kind of assess how things are going, right? And so that's an ongoing challenge.
I'm like struggling I'm not going to ask another question, but if there's anything from the audience, we do have some amount of time left. I am now, since we are right about at time, I'm going to bring back my deck, show everybody our contact information. I will speak for the whole group and say questions are also welcome via email. We do have 15 minutes until the next session. So if there are any remaining questions, do please jump in. But I think with that, I might close it out. Are there any thoughts from the panelists you want to kind of close out with, or any questions for each other? 30 seconds. Thank you again for coming, especially my panelists. Excellent. This is great. Huge respect for the expertise that we have gathered in the room. No joke, that product development cycle is a huge amount of work. And you can only really come at it if you do know what's ahead of you and what's behind you, right? So even if you enter a project sort of in the middle, the respect for the process and knowing how much went into everything, I think is huge. So thank you to everyone. Thank you for the audience. And I will see people hopefully in a later session. Hope you're enjoying FedCASIC. Thank you from the committee as well. I'm a FedCASIC organizer. So.
Welcome and thank you for standing by. At this time, all attendees are in a listen-only mode until the question and answer period. This webinar is being recorded and may be posted publicly. If you have any objections, you may disconnect at this time. Now I'd like to turn the webinar over to Amy Thompson. Amy, you may begin.
Wonderful. Thank you, everyone. And hopefully you're here for session C3, Data Science Applications Text Analysis. We have a full lineup today, so I will jump right in. I'm going to give a brief introduction for each speaker. Please hold the questions till we'll have a time at the end for questions. As they occur to you, please put them in the chat and we'll be sure and bring them up. First, we have Monica Puerto. Monica is a data science manager from Accenture Federal who has a master's in data science and specializes in natural language processing. Monica is passionate about civic tech and consulting the government on ways machine learning can support processes. Take it away, Monica.
Thank you. It's great to be first this year. I was last year. So thanks for coming to my talk. And today we're going to be evaluating different speech to text transcription models. I'm a data scientist from Accenture Federal Services, and I'm going to present some of our work of the exposure we have had with speech to text modeling through the lens of data collected from the 2020 census. I want to thank my co-authors from Census Bureau for their support in this work on this slide. So today's objective is understanding what to consider when using speech-to-text technology. So the Census Questionnaire Assistance Program, which is where we analyzed the data from, also known as CQA, received over 4 million calls, which with permission were recorded, and over 7,000 agents facilitated those phone calls. They're also known as CSRs, and they answered questions about the 2020 census or took the survey response over the phone. The CQA supported over 16 languages, but 95% of the conversations were made in English, Spanish, or Mandarin. As you can see, the calls received were mostly in English. So let's look at the steps in a speech-to-text pipeline for evaluating this technology. So to evaluate a speech-to-text model, you must first start with a sample that is representative and diverse. So we sampled across English, Spanish, and Mandarin, the main 3 languages, across the different periods of the operation. So the census decennial was around from March to October, and that's when the CQA assistance program was facilitating support. So we sampled across those time periods. And then once we had our samples of audio calls, we then focus on pre-processing the audio quality before we input it into the model. So these are steps I would advise you in taking because with any modeling, it's largely influenced with the quality of your data. So the whole trash in and trash out concept. So we, in our research, benefited from normalizing the audio, removing long pauses, and transcribing the agent and the caller independently. We then tried out different speech-to-text modeling technologies. So we looked at more than one model. So I want you to think of them as different types of cars and also within the same brand, how some cars can differ. So like one car can have 2 cylinders versus 4 cylinders, and those are kind of like the parameters of the models. So models are not all built the same. I'm not going to get into the weeds of the different models because that's like a machine learning class, but I'm here to focus on how do we evaluate them even if they are built differently. So in order to evaluate them, you will need a human reference to compare the text transcribed by these models. So to create a reference, you need guidelines for your manual transcribers who are going to be transcribing manually the same audio files. So in order so we had to create these guidelines for all the manual transcribers to write in the same format. So after we eyeballed some outputs, we came up with these rules based on the patterns. So we needed to follow these certain conventions to match the machine transcript. So number one, no use of punctuation, proper use of accent marks, especially for non-English, spelling out the numbers and letters. So for example, like 2020 census, the numbers 2020 were spelled out. So filler words, these are the ums, hums, and ah, the pauses that people do in everyday language. So we established a shared document with the standardized spelling of these filler words. So once we have transcribed all our sample audio, we then compare to the model's outputs. So now we can calculate what we call word error rates, which are the standard on evaluating speech-to-text technology. So simply, it's taking the number of the words of the machine transcript and counting how many substitutions, insertions, and deletions does it take to get to the human manual transcript. So for example, let's look at this toy paraphrase example. So let's say we manually transcribed the agent side, and they said, welcome to 2020 census. Would you like information about the race categories? Let's say we had a speech-to-text model transcribe this instead. So I want you to notice that in this like light brown color are the misspellings. So census was misspelled, and then the model heard response versus race, and it inserted, there was one more word, so the more, which was not in the manual, so that needs to be deleted. And then the in purple on the manual transcription is missing from the speech-to-text model. So once we count all the words in the transcription from the machine, we have 13 words, and we need 2 substitutions, 1 deletion, and 1 insertion to get to the manual transcription. So thus, this toy example has a 31% word error rate. So to give you a better sense of some issues in transcription models that can actually inflate your word error rate, these are the 2 common issues in speech-to-text modeling that we have come across. Number 1, hallucinations. So these hallucinations are typical from large language model frameworks, and these are similar frameworks that models use that do generative AI. So these are large, deep learning models that are harder to understand and seem to hallucinate more often versus models that function more like a stochastic model. So like think like Markov chain, where they predict based on the sound of the audio versus the words that come beforehand. They don't tend to hallucinate, but they tend to misspell more. So a hallucination might inflate your word error rate more, but maybe you can create a function that deduplicates sentences once they find them. So other than hallucinations and misspellings, there are things you want to consider, such as number 1, cost. Some are free to the public versus some you might have to pay for. Number 2, there's different modeling frameworks and those influence different error types, like in the last slide. Like we saw more frameworks that are large deep learning models, especially that share the same framework for generative AI, tend to hallucinate more versus like a stochastic phonetic model tends to do more misspellings. Also think about the data these models have been trained on. So a lot of these models either have been trained on the same data. There's a large amount of like public audio out there, or maybe they have their own proprietary data to train on. And you have to ask yourself, is this data diverse for my purposes? Such as, is there data that can support a lot of accents? And we want to make sure that they're not behaving differently across demographics, especially if your population is very diverse. Not all models support all languages, especially open source. So models from big companies that are used to support large clients, let's say like in the call center or e-commerce, they're going to have more support on a variety of languages. So AWS, Microsoft Azure, and Google Research, etc., are big companies and can offer any type of language. So these are our takeaways from our research. So English transcription models are much farther along than non-English. So we saw word error rates range from 10% to 50% higher when we were transcribing Spanish and Mandarin. You also have to consider dialects that have more than one writing system. So in our instance, Mandarin has a traditional and simplified writing system. So can you specify in your model what writing system? In AWS, we could hard code traditional versus simplified versus an open source model we were comparing called Whisper, we could not. The agent side has a headset and that helps to produce a lot cleaner audio. So on average, the agent transcribed a lower word error rate than the caller, from 20 to 50% lower. There's more background noise with the caller, and there's obviously a more diversity and variation if you thought about, the millions of calls that we've had versus, 7,000 agents. Some models like OpenAI's Whisper perform poorly with long pauses, so it would stop transcribing. So we had to remove long pauses in order for it to keep going. And then it would also hallucinate. Some models leave filler words and others strip them out. So take that in consideration with your word error rate calculations. So now that you know about word error rate and model issues and some of our learnings, use the speech-to-text evaluation method to make your best transcription pipeline for your business use cases. So you're not transcribing lots of audio to just transcribe. You are hoping to make decisions or gain understanding of them. I would like you to consider these ethical questions for your business case. So what kind of decision is made from this data? And what is the appropriate amount of margin of error transcription that I'm willing to accept? So number one, do I have enough data to be representative of my sample or my population? Will a decision be made from this data that is impacting someone? If so, is there any difference between word error rates by demographics? Is there enough information to gather insights? So let's think of these two scenarios. One, where you're trying to gain insights by making sense of over a large amount of recorded conversations and the different question groups summarized for machine learning, which is known as topic modeling. And another to help support training agents and automatically detecting if someone is adhering to the script provided to them, especially for survey responses. The data on the left, you need a lot of data if you're trying to represent millions of calls. However, you might be more comfortable with higher transcription word error rates if you can still understand question themes and groupings. In this image is an example of 3 clusters of conversations we found in our data. Number 1, questions about census visits during the non-response follow-up field operations. Number 2, race and origin questions about the survey instrument wording. And number 3, questions or issues completing the survey instrument online. Whereas on the right, you might just need a sample of 5 to 10 calls per agent to see who needs training and is underperforming. The agents have to read scripts word for word for statistic purposes. And it's federal approved languages. So machine learning can help aggregate all their calls and discern who needs training on script adherence. However, you are dealing with a decision at the human level, and you would want to have the lower word error rates in this scenario versus the scenario on the left, and optimal audio quality to approximate reality and be fair. So in conclusion, to determine your best speech-to-text model for your use case, number 1, make sure you have optimal and representative audio quality. Consider your model choice with cost, the data that was previously trained on, language support, etc. And also ethical considerations for your decision-making and insights use case. I just want to take my last minute to shout out to all of our manual transcribers in this slide who listened to many audio segments in English, Spanish, and Mandarin, and transcribed depending on the language they were fluent in. So this is definitely a team effort.
All right, thank you very much, Monica. I'm going to go ahead and introduce Haley Hunter-Zink. Haley, if you'd like to set up your slides as I do so. Haley Hunter-Zink is a data scientist in the Center for Optimization and Data Science at the U.S. Census Bureau, which she joined in 2022. She holds a PhD in computational biology from Cornell University and has previously worked at the Veterans Health Administration, developing machine learning models for electronic health record data. Her current work includes applying natural language processing techniques and machine learning to web scraping, record linkage, and processing of free text responses for federal surveys. Take it away, Haley.
Couldn't see the screen anymore, so can you hear me all right?
Hold on, we can't see your slides. I think you're sharing the wrong screen.
I had to. Can you see them now?
Yes.
Okay. Now I'll flip them. Do you see the slide view?
Perfect.
Okay, awesome. Thank you so much. So thank you for the introduction, giving me the opportunity to present. So I'm a data scientist in CODS, and I was going to tell you a little bit about how we're using some machine learning approaches to autocode open text responses, especially when they're including rare words. So just quick disclaimers, the opinions expressed here are my own, and this presentation does not contain any sensitive information. All the data is synthetically generated. So the main problem we want to solve is that there are free text responses to categorical questions in many different federal surveys. And so the form that these usually take is there's going to be some question, there's going to be a finite number of defined responses, and then many times there'll be a sort of other checkbox in which the respondent can expand with additional details. So some examples of these include the decennial census. When asking about a person's race, we'll say mark one or more of the boxes and print additional details. And an example of the 2020 decennial census questionnaire for this question is shown on the right. But it occurs in many other surveys as well. So for example, the economic census asks about primary business or activity, where you have select a sector, they'll provide some options, but you can also specify another. And then just a final example, the National Survey of College Graduates will ask, among many other things, what type of educational institution did you get your degree from? And you can either mark one or specify something else in free text. So underlying these categorical questions, there'll be a sort of subset of the answers of which you could check a box, but underlying all of them is usually a standardized set of codes in an ontology or a list that provides a set of all the possible conceptual answers to this question that has been defined by the survey organizers. So for example, in the 2020 decennial census, for the race and ethnicity questions, the 2020 decennial followed the guidelines published by the Office of Management and Budget, or OMB, for the categories for collecting race and ethnicity data, of which respondents could select one or more. But after creating this sort of free text field, the data to be ingested in sort of downstream processes and into research data products, it needs to be standardized. And so once these free text responses were received, they needed to be matched to the underlying set of codes and categories. And so there were two major ways that this was done in the 2020. So number one was through a sort of automated coding procedure, which consisted mostly of a dictionary lookup. So essentially we have a list of responses, we have a list of their sort of corresponding standardized codes. And if we find an exact match between our response and the dictionary, we're going to assign that code to the response. However, that didn't work for every response. And so there was a secondary path where expert coders who were specially trained manually annotated those responses. So for a operation of the size and scale of the 2020 decennial census, you can appreciate that even if there is a very small fraction of responses going through the second pathway, this can actually add up to a very large number of responses that need to be manually coded. And so they're interested in seeing if they could extend the automated coding performance or automated coding procedure to reduce and augment expert review. However, there are a number of challenges that need to be addressed that make this problem particularly complicated for auto coding. One is that there are sometimes thousands of different outcome codes that are all possible responses. There's also a large number of rare terms that may not be frequently seen in other contexts or even on the web. There's also a heterogeneity of responses. So one given code may have only a few ways that it will be expressed by respondents, and others may have many different codes. And finally, there may be inconsistent coverage. So some some codes or some concepts related to those codes may be frequently referenced by respondents, whereas others we may have very little information or very few examples in order to be able to determine what patterns map those responses to the codes. So to address these challenges, we wanted to see if we could use some machine learning techniques to classify these free text responses to categorical questions, given these challenges. And so for this particular problem, we're going to make it really generic, and we're going to structure it as a supervised multi-label classification problem. So to break that down a little bit, for the supervised, it means we have label training data available, we have our responses, and we have the codes that correspond to those responses. For the multi-label classification, we're essentially going to treat each possible code as an outcome, and then our prediction value for each one of those outcomes will either be 0 or 1. And this allows us to assign any possible subset of the codes to a given response. And just a quick note, this is distinct from a multi-class classification problem in which we would have a single outcome that had multiple values. So to make that a little less abstract, we're just going to generate a simulated data set on which we're going to do our benchmarking. And each of the generated samples is going to look like something like the example below. So we're going to have some response, essentially of made up words. And then we're going to have it mapped to a matrix that has each code of which the values are either 0 or 1, indicating whether that code adheres to that response. So first, to create the simulated data set, we're going to generate an ontology of codes. Essentially, we're going to define a number of levels in this ontology. And for each level, each node is going to produce a certain number of children down until we reach the final and most granular level of the ontology, which represents the codes that we actually want to map to all of our responses. So we've generated a set of codes or underlying concepts that we want to assign to responses, but now we actually have to assign terms or ways that they would be expressed in the real free text response. So we didn't want to use real words. We want to focus on sort of rare words, and the best way we could make rare words is essentially to make up words. And so the way that we did this is that we just downloaded a public corpus and we tallied character to character transitions to construct things that perhaps weren't words, but maybe looked something like words. And so an example, or a simplified example of that transition diagram is shown on the right with just 3 characters, C, A, and T, and sampling through this diagram for as many samples as we want to generate, we'll create a term on each sampling. And some examples of the generated terms from this particular transition diagram are shown below. So we have codes and we have terms, and now we have to associate the terms with the codes. And so to get at the sort of heterogeneity angle, we were going to sample a certain number of unique terms from our generator with each code. And so over our simulated data set of around 10,000 samples for responses, we have, with our actual codes, we have a distribution of the number of terms assigned to each code, which is shown on the left, which has a median of about 2 associated terms. But as you can see, there's definitely some codes that have a larger number of terms, and one example of that is shown on the right. The C112 has 4 example terms associated with it. So we have codes, we have terms, we've associated the terms with the codes, and now we actually have to generate our samples and our responses. And so the first thing we do for each sample is to randomly generate a number of codes or concepts that would be expressed in that particular sample's response. And the distribution is shown on the left. So for the majority of samples, there's only going to be about 1 or 2 codes or 1 or 2 concepts expressed in that response. Once we've selected the codes, we then randomly select terms associated with those codes to construct the full response, and then put it together, just concatenate it together to construct a full response for that sample. So after we've done all of this, we can look at our ontology. So if we go down from levels 1 to 4, which is the most granular, at the most granular level, at the level that we actually want to predict, we have about 81 codes in our simulated ontology. And then for each of these codes, we can look in our sample data set and look at the coverage of each one of those codes. And that distribution is shown on the right, where we have about 240 responses per code. So you'll notice that this distribution is fairly normal looking. This is fairly unrealistic. For the vast majority of real actual data sets, this might look more exponential, where we have many codes that have few responses corresponding to them and a few outliers with many responses. So just keep in mind, this is a fairly unrealistic simulated data set. Okay, so we've constructed our data set, and now we actually want to be able to do the actual auto-coding. So as a baseline, we're going to just implement a very simple form of this sort of dictionary lookup or string matching. So here for each particular response, we're just going to tokenize it. And for each token, we're going to compare to a standardized dictionary that maps codes to terms. And we're going to calculate the string similarity between each token of that response and each term associated with a code in the dictionary. If the string similarity exceeds a particular threshold, then we're just going to assign that code to that response. And so just an example of how that works is on the right. We have our dictionary of codes and terms, and then we have our response tokenized by spaces. And we're just looking at the string similarity between each pair of code terms and the token in the actual response. And we just assign the two codes that exceed the string similarity threshold of 0.8. So we can move on and try some classical machine learning approaches. So here we're going to represent each response as a count of character bigrams. So essentially we're going to have a fixed length vector where each column represents a particular pair of characters. And we're just going to count in the response itself how many times that pair of characters occurs. And then we'll have a sort of fixed length vector that we can calculate for every single response for later ingestion into a classical machine learning classifier, for example, such as a multi-layer perceptron. And so we can use all of our training data to then train this multi-layer perceptron with the simple sort of character count bigram representation of the text. And then we can take it one step further and we can use some more recent transformer-based text classification methods. So here we'll also be transforming our free text responses into a vector. But here we're going to use some of these pre-trained transformers, which as opposed to using a fixed length vector that just counts up character bigrams, now these vectors will hopefully incorporate some of the sort of semantic meaning of these free text responses. So what that means is that even if two responses share very few words and share very few characters, if their meaning is similar, then the vector representations within these internal models should be somewhat similar. So we're going to fine tune sort of two different types of these transformer models. One, we're just going to fine tune a sort of BERT-based model with our particular classification task. The other will encode our free text responses with a sentence transformer and then just ingest that into another classical machine learning model. And then we have to, when we're going to benchmark, we're actually going to evaluate these. So we're going to use some pretty standard machine learning performance metrics, the F1 score, precision, and recall. All of these values just range from 0 to 1. The larger the value, the greater the performance. And the values can be calculated either for each outcome individually or averaged over all of the outcomes. Just more specifically, the F1 score is the harmonic mean of precision and recall, where precision is out of how many samples are actually predicted as a label, how many actually are truly that label. Whereas recall flips it around and says, okay, out of how many of the samples actually truly are that label, how many do we predict as that label? So we ran our sort of our 4 different machine learning methodologies plus, or 3 different machine learning methodologies plus the sort of dictionary lookup autocoder on our simulated data set. Overall, the transformer with a sort of Roberta, a modified BERT training transformer, performs best, but it actually, in the context of our simulated data set with many rare words, does not drastically outperform a more basic text representation and a classical machine learning model. If we look at the bar chart on the left, here we just have recall, precision, and F1 score on the x-axis, and each one of the colors represents our different methodology. The major decline in performance is for the autocoder, where we're using just this dictionary lookup. Although the dictionary lookup has a very high recall, where we suffer is in precision. And that's just because we're assigning a lot of codes with our fixed sort of string similarity threshold that shouldn't actually be assigned to that given response. But the other machine learning algorithms work fairly similarly, but just again to note, this is an artifact of our particular data set where we're concentrating on so-called rare, and in this case, completely made up words for which transformers, because they're trained on sort of large corpora of real documents, are not expected to create the same sort of gains you would see in actual real English language terms or other language terms. On the right is just for our best performing model, the distribution of all of our performance metrics. You can see that it's centered around 1, the sort of perfect performance, but there is some density sort of for lower metric values indicating that some codes or the models may be able to predict outcomes for some codes better than others. So if we're bringing this back to the real world, there are still sort of ongoing challenges that we would need to address with these models. The first, for race and ethnicity coding in particular, is that the guidelines are changing. So we need to be able to either map our sort of previous supervised data and labels to the new standard and retrain our models to incorporate those changing guidelines. As I think has been discussed in other sessions, we also deal with model drift and bias, which may affect our performance. So for model drift, this is just the concept that as the data you apply gets further and further away from the data that you originally trained your model on, you'll see performance suffer just because of changing patterns. In terms of the decennial census, this only happens once every 10 years, so we are going to need to be able to find other data sets for which we can sort of fine-tune these models in the interim. Bias is also a concern, especially for race and ethnicity coding. We may have a lot of representation from some particular concepts and not from others, and we need to make sure that to monitor that performance and ensure that the model is not underperforming in particular areas. And this goes both for our own labeled training data sets for fine tuning, as well as any sort of pre-trained models that we're using in the pipeline. So overall, even on our very simple simulated data set, machine learning models seem to provide advantages over dictionary lookups. Also, secondly, and just in the context of sort of auto vocabulary, in our case, made up words, transformer models may not provide little benefit over sort of basic text representations. This, of course, will not be true if you're incorporating actual language within your text responses. So just keep that in mind. But at the same time, if your corpus contains many vocabulary words that are specific or not seen outside the context of a given survey or other application, and in particular, if they are not well covered in a sort of general web search, and many of these sort of transformer models were trained on sort of a lot of web scrape data. If you're using a lot of vocabulary words that wouldn't be well represented in that context, it might be something to keep in mind in terms of how well these models will perform on your given use case. And overall, we're continuing just to explore and benchmark different modeling strategies to improve performance for these applications. So with that, I'd just like to acknowledge and thank all of my collaborators, and I'm happy to take questions later. So thank you.
Wonderful. Thank you very much, Haley. Next, we'll have Curtis Chapman. Curtis, if you'd like to go ahead and get started setting up the slides while I introduce you. Curtis is a survey statistician and a recent hire in the Center for Behavioral Science Methods and ADRM, which I'm interested to know what that stands for. His work primarily leverages large census and administrative record data sets towards research goals using machine learning and natural language processing. Take it away, Curtis.
All right, ADRM is another research section of census. I am going
Curtis,
to be...
I don't see your slide yet.
Oh, I'm sorry, I didn't share. I just pulled up my slides. Okay, can you see them now?
Yes.
Wonderful. Okay, so I'm Curtis Chapman. Thanks for joining us. This talk is geared a bit more toward those who aren't familiar with machine learning. So those who are might be more familiar with this. But really what it's about is exploring rare topics in large unstructured text data. We call it looking for the needle in the haystack. So in census data, sometimes you're working with, or in survey research, you're sometimes working with text data. So this is often in the form of open response questions, like my colleagues have talked about. and sometimes in the form of conversation transcripts, say from interviews or focus groups or what have you. So the data you have might look something like this. This is a small data set from Kaggle that's an open answer question on why people are studying data science. And you don't need to look over the whole thing. This is just to give you an example of what a data set might look like. And a typical goal with data like this is to extract common response categories, get big, broad categories. Things like I'm studying data science for my job or for the challenge of it, for the passion that I have for it. And approaching this sort of goal is not easy in and of itself, but the methods are there and readily available. You can do simple things. Alternatively, you might have a goal like finding a rare category. Say you're in cybersecurity and you have tens of thousands of responses to this question, but you want to find those rare cases where somebody is studying data science for nefarious purposes. Now, this is a really silly toy example, but it puts the point to it that if you're looking for a rare topic, the methods are less straightforward for going about it. And that's what I'm going to give you an example of here today. And to sort of outline where this might be useful, I'll give you the example of the undercount of young children in the CQA data that Monica was just talking about. So children under 5 years old are consistently undercounted in the census compared to demographic analyses. And the 2020 census questionnaire assistance data is a useful data set for researching what's going on here. So CQA was a telephone support line that had nearly 5 million recorded calls. Things like, I already submitted my census forms, why am I still being visited? Or how do I answer the race question? And for another project, about 91,000 calls were transcribed. You saw Monica's talk. What's interesting here is that the undercount of young children wasn't a main topic that was logged by customer service representatives, but the CQA data could help to understand how confusion contributes to that undercount. So this is one of the main topics that I'll talk about today, one of three. So how do we approach this? The first most obvious pass would be to just look for keywords. So find all transcripts that have certain keywords related to your topic. This is useful because you might not know what those transcripts should look like. I mean, what are people actually calling about? That was the question that we had. What are people calling about related to the undercount of young children? What does that look like? And then the second thing you could see with this method is, well, will keywords alone work? Will I find everything I'm looking for just using keywords? This helps to understand the problem as well as to try and solve it. So the topics that I'll be looking at are the undercount of young children, which I've already talked about, death affecting vacancy or count in the census, and Canadian citizenship affecting vacancy or count. And the method is from those 91,000 transcribed calls to take the 2/3 or so that were labeled as general assistance calls or technical issue calls, and then first to search for transcripts with topic-related keywords, which I'll show you on the next slide. And then for each transcript, just say, is this related to the topic? Yes or no, 1 or 0. So the keywords looked something like this. For the undercount of young children topic, there were lots and lots of different keywords, and we found kind of too many transcripts to be tractable for a short-term research project. So instead, we restricted to a subset of those keywords and found and coded about 400 transcripts for the presence of that topic. For the death topic, the keywords are a bit more obvious: dead, died, death, etc. Again, we found too many to be tractable to search through in a short amount of time, so we coded 400 of those that were randomly sampled from the set. And then for the Canadian topic, it was even easier: Canada, Canadian, and we found 300 transcripts and coded all of them. So we had, this table shows what we searched and what the results were. So each row is a topic, and each row has the rough number of total that we looked at, and then the rough number that we found that were related to that topic. So you can see that about a quarter of the undercount related keyword transcripts were actually related to that topic, almost half of the death related transcripts, and 2/3 of the Canadian keyword related transcripts. Good. right? So we have a good idea of what these transcripts look like from this. For the undercount, you have something like, what do you do when you have 50-50 custody? So the kid is 50% in one home and 50% in another. You have something like, my mom received some of your census papers and she's passed away. I wanted to let you know you can take her name off the list. Or something like, I'm a Canadian resident owning property here in Florida. We're only here seasonally. Do I have to complete the census? Where do we go from here? Is this all of the transcripts related to our topics? No, right? We didn't even look at all of the keyword matching transcripts that we found. We could do that, but there are a couple of other issues. One of them is, well, did we miss any keywords or phrases? We could bring subject matter experts in to like try and be exhaustive about that. But even then, we can't really be sure that we caught all of them. And something more important here is another issue, which is maybe some transcripts aren't easily matched by keywords. I'll only go through the first example here, but to illustrate it, take my wife and I share our kids half the time. Should I count them or should she? So each one of these highlighted phrases could be phrased in lots of different types of ways, right? And not only that, if you searched for the terms in here like share or half the time, you're going to find a lot more noise than signal. So we want a way to get at the multiple meanings across a set of words, or the single meaning that lots of sets of words could have. This is how we search the remaining 90,000 plus transcripts. And this is a good machine learning project or problem because we already have labeled data sets for these three topics. So the general approach in our next step is to use machine learning to take the set of labeled transcripts, zeros and ones for each different topic, and predict similar transcripts. The process in very high level terms looks like this. You have a data set where each row is a transcript and you have a label for it of whether it belongs to the topic. Then you create a model that learns the patterns in what in the transcript is related to something being a 0 or a 1, being related to the topic or not. And then use the patterns that it learned to predict on new transcripts. So you don't have the labels for those, but you have predictions of what they might be. And these can come in multiple forms. So to peer into this a little bit, machine learning models require numerical data. So you have to take the words and transform them into numbers. And that's what we did. We did it in a very common natural language processing way with a large language model that tries to preserve meaning information. And you end up getting something like this, where again, each row is a transcript, but now each column is a sort of abstracted feature of the words that are in the transcript. That somehow preserves the semantics of it, the meaning of it. And you can see that you can have quite a lot of these columns depending on the type of model you use. So for each of these three different topics, we trained and tuned a classifier model, specifically an XGBoost model, on the labeled transcripts, and then predicted on the remaining set of 90,000 plus transcripts. So what you get out of a model like this for predictions is a set of probabilities that that a transcript belongs to the topic or not, ranging from 0 to 1. And what you do with that data is up to you. You have to determine what probability is high enough for you to think the model actually thinks this belongs to your topic. So you could use an arbitrary thing like, okay, if the model has a 0.5 probability or higher, I'm going to call that yes, it belongs to my topic. But a better way is to look at the distribution of probabilities that you get out of it. So take the undercount topic here. This ranges from 0 to 1 probability on the x-axis here. And you can see that most of the transcripts were predicted to not be related to this topic, right? But if you zoom in, you can see that it goes down, 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 down in probability, or in the amount that's predicted to have the probability, but then it goes back up again. We have a second mode in the distribution here, and that means we can find a line in between those different modes that is likely to separate what the model thinks is related to your topic versus isn't. And so we decided on that threshold based on a reasonable point between the two modes, and we did that for each different topic. You can see that each topic had a unique cutoff point, and it also had a unique range of probabilities that it predicted, which may be related to our results later. And we'll talk about that. So what this looks like is I've put into this table, so these different probability cutoffs, and then we can see the number that fell above that cutoff. And I'm going to illustrate this with this probability distribution for the Canada topic. So the probability cutoff is that red dotted line there. And then the number above the cutoff is the set of the distribution that goes to the right of that line. You can see that for the different topics, it vastly differed, right? So the undercount topic, it was a very reasonable number that was above the cutoff. But for the other two, it was thousands, which is not only unlikely, but also, again, untractable. So what we did was to take a sample of those, and we made it the same across all of them for multiple reasons, largely for consistency. But in the case of the undercount, we took the highest probabilities plus some beyond the line, which helps us also know, did we set the threshold at the right point? And then we assessed those for, is the model right about these transcripts? Do they actually belong to the category that we think they do because of our model, that the model thinks we do? And this is what the result was. So we found 20 additional transcripts that were related to the undercount topic, but none of the transcripts that we looked at were related to the death or Canada topics. So what can we say about this? First, the undercount model did pretty well. I mean, it's useful. It's only 10% accurate in these ones that we assess, but that still saves us a lot of work, right? We didn't have to look through 90,000 transcripts. We only looked through 200, and we found 20 additional transcripts. For the other models, not so much. And there's multiple reasons that this could have happened. One could be that we didn't look at all the sample. Again, like the keyword thing. Maybe if we looked at all 7,800 of the death transcripts, 78 of them or 780 of them would have been death related. It could also be that keywords are sufficient for topics like death related account or being a Canadian citizen, because something like Canadian citizen, you're likely to mention the word Canada, right? Or at least snowbird or something like this. So some topics that you're looking for might be better or worse suited to this sort of method. There's also ways that this type of model can be improved. So the model I just told you about used the full labeled transcripts to predict similar transcripts. But there are some drawbacks in this particular kind of data set. So our transcripts can be really long. This is one on the longer end, and I'm only looking at ones in the 90,000+ that weren't in the keyword data set for Canada. So the median of those 90,000 was 140 words long, and at the higher end was over 1,000 words. This one's over 1,000 words. When you have long transcripts like this, multiple topics are broached. So you can see the highlighted stuff here is related to the topic at hand, but the red stuff is not actually. And this is true even in stuff closer to the median, even in transcripts closer to the median size. So what do we do here? To improve this model, we could match shorter texts. We'd have a less diluted signal. If you think about all of the words that are in here, only a small portion of them are signal, so the rest is noise. We could take the most topic relevant sets of words and say, these are related to our topic. And do matching based on those. And then when we predict the transcripts, we can predict on smaller sets of the transcripts. So sets of 100 words or something like this, or 50 words. And if you find a single snippet within a larger transcript that's related to your topic, then you know that that transcript probably touched on your topic. So the general method that I went over, even without doing these revisions, could be really useful for data sets that have smaller amounts of text, right? But the revised method might be more useful for stuff like this, where there is a lot of noise in there and you're trying to get small snippets of signal out of something. With that, I'd like to thank my collaborators. Monica Puerto helped me with some of the data science aspects of this, advising on that. And Crystal Hernandez was a great help with coding the transcripts. I needed some extra coding help, and it was a lot of work, and she helped a lot. And I'm glad to take questions once we are through with the session. Thank you.
Wonderful. Thank you, Curtis. Next up, we have Dr. Joelle Abramowitz. Joelle, if you'd like to get your slides ready while I introduce you. Dr. Abramowitz is an associate research scientist at the University of Michigan's Institute for Social Research and co-director of the Michigan Federal Statistical Research Data Center. She completed her PhD in economics in 2013 at the University of Washington. Her research examines the effects of different policies and environmental factors on individuals' major life decisions and well-being, including on self-employment, health insurance, and medical out-of-pocket expenditures, as well as bigger picture effects on outcomes such as marriage, fertility, work, and mortality. Wonderful. Take it away.
Thanks so much, Amy. So thank you for having me. Thank you, everyone, for attending. Today I'll be talking about using machine learning to better understand self-employment in the panel study of income dynamics, which is a survey that we conduct here at Michigan. And so really the impetus for this work is that self-employment is difficult to measure. It includes a breadth of work arrangements with very different characteristics and effects on well-being. So just to give you an example of different kinds of self-employment we might see, someone could be an independent contractor for a limousine company, or they could be an owner-operator of taxi cabs. They could be informally driving as a side hustle, or they could be a Lyft driver. And those are all examples of self-employed people working in the transportation industry, but doing very different kinds of jobs with very different work responsibilities and potentially effects, on their well-being and their income. And the problem is that in existing administrative data and household surveys, we see that they can suffer from incomplete coverage of the workforce or insufficient detail in work arrangements. Part of the problem is that in administrative records, we don't capture employment that's related to income that's not reported to tax authorities, and we don't have a lot of the other information that we might want on those individuals about their demographics or their well-being. And in household surveys, they're often cross-sectional. They don't probe about detailed employment characteristics, and they focus on primary jobs only. And as a result, substantial amounts of work are not being captured, or they're inaccurately captured. And we actually see discrepancies across surveys, between surveys, and administrative data in identifying trends in self-employment. And so we try to address these issues by producing novel data to enable understanding trends in the nature and prevalence of different kinds of work arrangements. As I mentioned, we use the Panel Study of Income Dynamics, or PSID for short. It is a longitudinal data set following families over time, with over 10,000 families and 24,000 individuals. And in addition to the standard categorical questions about work, it also asks respondents open-ended questions about their job industry, occupation, and title, along with employer names. And that is asked for all work for which they were paid since the last interview 2 years prior. And we use machine learning of the open-ended questions to classify respondents' jobs by type of work arrangement. So just to give you a sense of what the PSID asks about these work arrangements, the interviewer would ask a respondent, I'd like to know about all of the work for money that you have done since January 1st of 2 years ago. Please include self-employment and any other kind of work that you have done for pay. Start with any job that you had during this time. What is the name of this employer? What is the official title of your job? In your work, what is your occupation? What sort of work do you do? What are your most important activities or duties? And what kind of business or industry is that in? So we use those narratives that respondents answer to each of those questions. Respondents typically answer with around 3 to 4 sentences, and those would traditionally be used, or the reason they're asked is to be able to code industry and occupation. But here we're using them in this different application where we want to understand these kinds of self-employment that wouldn't otherwise be captured. So we use these narratives and the employer names along with machine learning to classify the work arrangements. We start with about 170,000 narratives over the waves of the survey that we're using. We first had 2 individuals open code a small subset of the narrative, so a few hundred, to identify common themes and develop a classification schema. And then using that schema, 30% of the data was hand-coded, and we had 2 individuals review each record, and then a third adjudicate any discrepancies. Then we used machine learning to classify the remainder of the data. This was the schema that we developed based on the open coding. As you can see, the categories that we're interested in are platform gig work, informal self-employment, so that would be like doing odd jobs, working as a handyman, a freelancer. Then we identify formal self-employment, so this would be working more as an independent contractor. We separately identify people who say they're business owners or presidents. And we also see a category of people who say they're self-employed and they manage a business. We lump those together. And then separately, we identify employees. So we're looking at all job reports. So we're also seeing wage and salaried employment. And so we identify those separately, and we separately identify those who are short-term or contingent workers from those who aren't. So to do this, we use machine learning. First, in step 1, we do training. The machine learning algorithms are trained on label data, in which each narrative is assigned one of the 7 schema categories. Next, we evaluate the models, and then we implement the models to predict labels for the new narratives that don't have labels. We've tested these models with both more traditional machine learning models, as well as we also use BERT. So for our BERT models, the classifier is trained on a vector of tokens encoded by a pre-trained language model, BERT, which is trained on a huge corpus to predict which word would occur after a sequence of words. And so we use both the traditional and the BERT predictions. And so here you can just see some of the precision and recall numbers for each of the categories, and we show them for both the traditional models, that's the base method, and then for BERT. And you can see that for our categories with the largest shares of narratives, which are outlined, that we do see in general better performance with the BERT model than with traditional models. So we apply the prediction onto our target data set of about 120,000 narratives. You can see here some of the details about how we implemented that. And then for those for which the probability scores were less than 0.95, we passed those back to human coders for manual labeling. And that ended up being about 11,000 narratives. If we had used a different cutoff like 0.9 or 0.85, you can see that those would have been a little bit lower. One challenge that I want to just highlight that we encountered was implementing the approach in an internet-free environment. And I'm interested to hear from the other presenters about how they might have encountered this on the federal side. But certainly, we here at Michigan are very concerned about maintaining respondent confidentiality, and so since these survey narratives are highly classified, they could reveal personal identifiable information about respondents' employers. So we're not permitted to implement the approach in an internet-enabled environment. And so the solution that we identified here was to apply the approach on a dumb machine that did not have access to the internet. We had to do that in a secure facility, which is basically a closet that my collaborator, Jin-Sa Kim, implemented the models on. And we had to develop some implementation protocols to be able to transfer the data onto that machine and then off of it. And then we were required that after implementation, the machine was wiped. But the result of all these efforts is a new variable with these schema categories. Or by using machine learning, we can do this at scale in a way that's replicable as we have new ways of data, certainly as this is a longitudinal survey. And we're able now to use this variable for research, and we're making it available publicly for use by other researchers, whereas the narratives can really not be made available in a public way for the reasons I mentioned. And so I want to emphasize that you could use this approach to look at other characteristics of these narratives and other narratives. And so I'll just share some of our findings that we're excited about that we're able to see by using these models. So here, when we look at different kinds of self-employment, we can see in panel A that, if we hadn't been able to implement these methods, we would just think of self-employment as one homogeneous group of types of work, but we know that it's not. And so here, when we break it out into these different categories and we kind of combine some together, when we compare informal self-employment and formal self-employment, we can see very divergent trends over time. And by using this method, we're able to identify these differences. And we see that on the left for people's main jobs. We see similar patterns on the right when we think about people's secondary jobs. And just to show you, I think this is pretty cool about what we can see about the kinds of work that people are doing across the income distribution. Here we can see that people both at the lower end of the income distribution and higher end are both engaging in more self-employment. What we can see from this figure is that it's very different kinds of self-employment. That for those at the lower end, it's mostly informal self-employment as a primary job. Whereas the share of people at the higher end of the income distribution doing that kind of work is much smaller. And they're mostly engaged in more either formal self-employment or business ownership. And we see similar kinds of differences when we look by sex and by age, that we see males tend to do more self-employment on average than females. We see that self-employment increases with age. But again, we see very interesting differences, across these categories, that women appear to be doing more primarily informal self-employment than we see for men. So, what do we learn from this? We identify otherwise masked heterogeneity in self-employment work arrangements. By using this approach, we can implement these methods at scale in a way that's replicable for classifying future waves of data. We're making these data available publicly. This is one survey that we've implemented this approach on. We've also implemented it on another Michigan survey, the Health and Retirement Study. And we've actually been able to revise that approach based on lessons that we've learned from implementing it on the PSID. As I mentioned, we could use similar approaches to look at other characteristics of interest in these data on work, as well as other kinds of narrative data that we have in the PSID and other surveys. And one thing that we're really thinking about is, now that we have these technologies, how can we think about different ways that we could ask survey questions that we might not have been able to do before? So for example, could we ask more guided, open-ended questions that we could use these methods on, that then would give us more flexible answers that might be useful over time as our areas of interest change? And one point that I really want to highlight is that, and I think this has come up in many other talks today, that this preliminary work is really important, not just to know what we can do, but to know what the limitations of these approaches are and how we think about those going forward. So I'll stop there, and I'm happy to hear any questions or feedback when we get to the end of the session.
Wonderful. Thank you very much. Makes me think of the self-employment I might have done in the past. Our last speaker, last but not least, is Gerald Thomas. Gerald, if you'd like to get set up while I go ahead and introduce you. Gerald is one of the data scientists in the Office of Compensation of Working Conditions at BLS. He has been working at BLS since September of 2022, and prior to working at BLS, Gerald previously worked as a contractor supporting defense and non-defense federal agencies. His academic backgrounds include a Master of Business Administration and a Master of Science in Data Science from Texas Tech University. And we can see your slides. Take it away. I can't hear you though, Gerald, if you're talking.
All right, I'm gonna go into presenter mode on my slide. So good morning, everyone. I did research on gender bias in the soy autocoder for the Office of Compensation and Working Conditions. The soy autocoder is a deep learning neural network model to provide supervised machine learning to classify non-fatal work-related injuries for non-federal government employees and the private sector. Aside from the recent executive order and the guidance from the Office of Management and Budget related to detecting gender bias and the responsible use of AI in the federal government, we are really concerned with producing gold standard, timely, accurate, and relevant statistics. And our office wants to ensure that any predictions we make are driven by the context of the narratives and not necessarily the use of any gender expressions within those narratives. We discovered that there are roughly 135,000 cases in the soy data that contains gender expressions. These gender expressions contain gender pronouns such as he or she, man, woman, and then there's also gender neutral pronouns such as they and them, and male and female salutations such as Mr., Mrs., Miss, or even sir or ma'am. And obviously these counts are not mutually exclusive because sometimes you might say there might be a case where Mr. So-and-so broke his arm in a narrative. We can see that there's a general breakdown for the distribution of this data. In order to produce a scientific explanation and really determine if gender pronouns and expressions are causing are impacting the predictions, we decided to drop all of the records that do not contain any gender pronouns and make predictions using cases that only contain any kind of gender expression, such as the 135 plus cases of soy data. To do this, we figured to provide a scientific method, we would substitute the use of a male gender expressions such as he, his, with either she or her, or they or their or they. And this allows us to run many experiments to see how the model makes predictions, as well as evaluating the predicted probabilities for that model. First, we made the baseline predictions without making any substitutions using the raw data. And this just establishes a baseline based off of a classification report using sklearn. Next, we substituted all gender expressions, whether there's female pronouns, female adjectives, gender neutral terms, or gender salutations with some gender neutral with the opposite pronoun. And so, for example, substituting Mrs. for Mr. or she for he in order to produce a reliable report. Then we did the same thing using all female predictions, using only female gender expressions such as she, her, woman, or Mrs. And then the last thing we did was use only gender neutral gender expressions. And we produced a classification using each substitution group or an experiment group and compared it to the baseline predictions. When we evaluated the predictions, we compared the predictions with substitution and no substitutions at all. And our goal is to really ensure that the predictions, the overall prediction, is generally the same as a baseline. We also evaluated the predicted probabilities for each of the predictions. And we're looking for essentially differences in the predicted probability. So the experiment group, using either all male, all female, or all gender neutral terms, minus the baseline group using no substitutions at all. What we found was minimal male bias. Male predictions were roughly 98 to 99% the same as a baseline. And for all 6 target variables that the soy autocoder predicted, there was an absolute difference of 0.01 to 0.001 percentage points. This is an extremely low number, and we can confirm that there's minimal bias in terms of predicted probabilities and the final prediction when we used all male pronouns. We did the same experiment using all female gender expressions. And again, the final predictions were 98 to 99% the same as a baseline. This is very similar to the male bias. However, there was a moderate increase between 2 and 9 percentage points in terms of predicted probabilities for all 6 target variables that the soy autocoder is trying to predict. Next, we evaluated gender neutral bias. Again, using all gender neutral gender expressions, including pronouns, there was 98 to 99% same predictions as a baseline. This is very promising, minimal gender neutral bias. Additionally, there was actually lower gender neutral bias for both all male gender expressions and all female gender expressions, with 0.0005 percentage points to 0.001 percentage points. In general, we can conclude that the soy autocoder gender expressions in the soy data has minimal impact on the final predictions made by the soy autocoder. There is a non-negligible impact using all female gender expressions on the predicted probabilities. However, this does not rise to the level that it impacts the final predictions using all female gender expressions. There are some different areas for future research. There is the LIME package using Python to really identify what the soy autocoder is making its predictions on. There's also areas for future research to look at automatically defaulting to use all gender neutral gender expressions during the pre-processing to reduce any gender bias for male gender terms, female gender term, and female gender terms due to the extremely low predicted probabilities. However, the disadvantage to this approach is the neural network for the soy autocoder depends on context, and substituting gender neutral terms might affect the context of the narratives. In general, I think it's safe to say that the soy autocoder neural network does not impact, the use of gender expressions does not impact the final predictions. I was the principal investigator for the gender bias investigation. If you have questions on model architecture for the soy autocoder neural network, my colleague Danny Todd can also answer questions, and we both collaborated on this project.
Wonderful. Thank you, Gerald. That was amazing. We now have about 15 minutes for some questions for the different presenters. Presenters, feel free to use your camera and answer questions, or however you feel most comfortable. I think, Monica, there was an early question for you from John Borman. I saw that you had answered it. I didn't know if maybe you would like to say anything more on the type of model that you used.
Yeah, that was a toy example, and words that are swapped out are more of like the large language models versus like the ones that use sound to predict are more of like the misspellings. And the question was like, how do you catch that? It's easier to catch the ones with like higher frequency, right? You can use bigrams or the trigrams. For smaller frequency, maybe using TF-IDF, right? And rank based on the weights to see like the more of the rare words being said, to see what are more common misspellings versus like rare misspellings. And obviously topic modeling can help understand the misspellings across groups, right? So a lot of different ways.
We have another question there, but I have a follow-up for you, Monica, on that one that I'm just gonna, since I can, throw the question in. So there was different types of language, right? So there was English and Spanish and Mandarin. Is that, do I remember? In terms of the types of challenges, so there was hallucinations and the misspellings, right? Was there anything significant in terms of the different language patterns or like the text that was used? As to one was more impacted with hallucinations or not, or did that not have an impact at all?
We saw hallucinations across all languages, so it's really like when it's tied to like the framework, you'll see it across languages. In terms of performance, the English word error rates, especially for the ones that are for more phonetically like use like the sound, were much better in English versus Spanish and Mandarin. And that's kind of been the case the last, I don't know, 15 years of natural language processing. English was always kind of been at the forefront, but now with large computing resources and you know, the need, and obviously US is like a melting pot. There has been advancements in non-English, but English is still definitely the doing better versus non-English languages.
Thank you. And just a reminder to the audience, if you have a question, you can throw it in the chat and we'll pick it up there. If you want to voice the question, you can raise your hand and we'll unmute you and give you that access. We did have another question in the chat, and that was for Haley regarding the histogram for the spaces. And I did see that you replied to that. I didn't know if you wanted to add anything on that.
Yeah, just to say that those histograms were sort of plotted over the performance metrics for each individual outcome. And the sort of point that we're trying to get with that was just that for most of the outcomes, we have good performance, but for some of them, the models aren't capturing. And sort of in the real data context, we usually see that as a sort of function of how many examples we have, how many responses we have for covering a code. And so we're just trying to look at that in the simulated data too. But thank you for the question.
I have a question for you, Haley, as well. So you had, and the other presenters, you guys are asking each other questions. That's great. So feel free to jump in and ask each other as well. Shoot, now I have to remember. Oh, the random, I believe the data was randomly generated or created. And I just wondered if there were any, and if there was, I apologize for missing it, if there was any like linguistic structure, right, that maybe was kind of built in, so distributions, because I know the models kind of pick up on that semantic structure that exists.
Yeah, so we actually specifically ignored the semantic structure. So yeah, there was no sort of semantic structure other than sort of having some character transition frequencies maybe sort of resemble. But we intentionally didn't mirror that because we were trying to look at sort of very short responses that often contain terms that wouldn't be widely seen sort of in context or on the World Wide Web. And so the way we simulated that sort of scenario was to essentially create simulated data that would ignore that context. And that indeed is why the transformers suffered in relative to some more classical sort of text representations.
I can check the chat real quick. Okay, I'm going to borrow this question from Joelle because I think it is very pertinent. And that was in terms of resources, in terms of like the modeling and how you went about building them and also where they were run from, like were there challenges, and this is for all of the speakers, presenters, that you had to take into account, because I think that's definitely a theme in a lot of the projects that are happening these days is how do we allocate the resources and how do we account for the privacy issues and things like that. Feel free to anybody jump on that.
I can answer. So we definitely don't use any models that have like an API, right, that can send like data back. And we just use packages that are I think approved by, I don't know if it's GSA, but packages that are approved, and then they're all in the secure environment. So they're all in, like we use AWS cloud services. So you would have to have like access and like roles and permissions in order to do that. And then we don't install any packages via the internet. We have like a mirror and previously downloaded packages. So everything, our data, our models are all in a secure closed environment.
I can speak to that as well. And especially I think, Joelle, you brought up sort of being in a confined environment without internet access. So yeah, it's the same as Monica. It's all sort of constrained. Everything goes through secure repositories. But I think the sort of issue that we have a lot of times is that many of these packages especially assume that you do have an internet connection. And so when you don't, things hang, and depending on the package, they may or may not tell you what's going on. And it can take some while to figure it out. And then also to actually resolve it and be able to actually run the model or the package locally, it usually is possible, but the documentation that tells you how is usually not super well written, just because in the vast majority of cases, people are operating in an environment where they will have internet access. So I think that's definitely been a challenge, and we've tried to document, at least internally, how we are sort of working our way around and fixing sort of the non-internet issues, so we can still use some of these great packages.
I've got a question for you, Curtis. I was like, either Gerald or Curtis, if you wanted to answer that as well, that was fine. But first, well, I have a comment and a question. Like those are some long texts that you're looking at in that data for sure. Like, oh my goodness. And you had mentioned different ways, maybe topic modeling, pulling the keywords. There's a lot of different approaches to that. Oh, wait, sorry. I'm like, what was my question? How did you decide on the topics? Because it seems like there's got to be a lot of different, so many options available. How did you narrow it down to those three?
The project grew out of a smaller, a project that was just around the undercount issue, actually. So that was an existing project when I arrived at Census in September that I took up from somebody who had left. And that by itself turned into a very, very big thing. The other topics were actually generated by my supervisor, since I didn't come from Census before. I came from academia. So I'm just getting familiar with really the types of topics that might be useful in this context. But if you have insights into that, I'd actually love to think about other things that this could apply to. That was one thing I was hoping FedCASIC would be able to reveal.
I don't at the moment, but I also have a lot of experience working with subject matter experts that they just have such background that they can like come up with some ideas, and it's amazing. I'm pausing to see if anybody else wants to jump in because I have questions. Okay, next question. This is like my own personal, like I just get to ask. Haley, I'm gonna make sure this is great. No, I'm sorry. This was Joel's presentation. For the different categories, for the labels, what was the distribution of it? So was it a balanced kind of label distribution, and how did you account for that or work with it?
Yeah, so, well, certainly in this set of data, most people are employees. Well, most jobs, we're doing this at the job level. So I want to say only about overall 20% or so of the narratives are self-employment. And then within those, we had a very small number of platform gig work, which is one of the categories we were really interested in, but it's just too small in our data set to get, a really large number. And then among the other categories, I think we see some more informal versus business ownership. So I guess I'm more of the subject matter expert, and my collaborator was handling the unbalanced nature of the data in that way. I can say on the platform gig work side that we, as I heard earlier, I guess about the soy, project, that we did a lot of manual work to, further like confirm those cases where it was just too small for the model to really do what we needed it to do.
I think we have time for maybe one more. Gerald, I wanted to ask one question if I have time to, but for the 135,000 example cases that you had, or what percentage of the soy data is that? Do most narratives have some sort of gendered terminology?
Yeah, so there's like 200,000 records for that year, because that data was collected for that was only 2022 data, and of the 2022 data, there's like 200. I think there's like just over 200,000 soy cases, and that's 135,000 with gender expressions.
I think that's more than I expected, but thinking of how often we use pronouns, that makes sense. And you had mentioned different ways in which, oh, this is for Gerald as well, sorry. You had mentioned different future let me rephrase that. Could you remove the gendered terms and run it that way? And kind of what do you think the result
So
might be?
the problem with removing gender expressions is because we're using a Hugging Face model as for the model architecture, that could impact the context. So there could be a case where gender expressions actually help better predict the data as it's intended. So for example, one of the target variables that we're trying to predict are body parts, body part injuries. And, you know, there's obvious anatomical differences between the genders. And when you eliminate gender expressions, it can impact the context of the narratives.
That's really interesting. I won't keep anyone where we are at time. Thank you to all the presenters again. Thank you to the audience. This has been a great session, and I look forward to seeing everyone at the next one tomorrow, all that good stuff for FedCASIC. Thank you again.
Thanks.
Welcome and thank you for standing by. At this time, all attendees are in a listen-only mode until the question and answer period. This webinar is being recorded and may be posted publicly. If you have any objections, you may disconnect at this time. Now I'd like to turn the webinar over to Fane Lineback. Fane, you may begin.
Good afternoon. I'm Fane Lineback. I'm the moderator of this session on alternative data sources. Thanks for joining us. As mentioned, at this time, all attendees are in listen-only mode. Attendees can submit written questions using the chat feature, which is at the bottom center or the right side of your WebEx screen. You can take a moment to locate that now. After all the presentations, we'll have time maybe for a few questions and answers, and you can submit those questions via chat to everyone or raise your hand to ask questions orally. I'll call on you and you'll be unmuted. And if you have any technical issues during the session, try exiting the session and rejoining using the WebEx browser version. So let me introduce our first presenter. Our first presenter is Amy Thompson, BLS. She is a member of the data science team in the Office of Prices and Living Conditions. Since joining the Bureau of Labor Statistics in 2022, Amy holds a PhD in Cognitive and Information Sciences from the University of California, Merced, and is passionate about lots of things related to data and data engineering. Thanks, Amy.
Wonderful. Thank you very much, Fane. Today, I would like, and thank you everybody for being here today. Today, I'd like to speak with you about an alternative data approach to index creation. All right, but first, what is alternative data? There are kind of many definitions kind of being thrown around, and so I wanted to get us all on the same page in that I'm speaking of alternative data with respect or in reference to already existing traditional data for a given task. So you can imagine that the framework already exists around traditional data, code already exists around that traditional data. And there are many forms of alternative data. You can think of geolocation data, social media data, clicks on web pages, sensors from Internet of Things, and also publicly available data. And one of the reasons that is such a good topic is that the alternative data market, the figure on the right, shows the growth that's predicted for this market. And so there's more and more alternative data every day. So when we think about alternative data, what how can we talk about it, or how can we think about it? And so there are many different ways, and this list of characteristics is by no means exhaustive, but there were very meaningful ones that I found through a lot of different research. And one of the things that I like is that there are both positive and negative aspects to these characteristics. So I just briefly want to go through these so that we can really get into a conversation about alternative data and how different ways in which it's used. So the first aspect of it is, of course, can I use it? Is it available? I'm working on something, and if I could only get this one data type, wouldn't it be great? And often it's not available. Perhaps it has cost associated with it. So that's a way in which that it's not available. It could also be just restricted or private data. So there are a lot of different aspects to the availability. I have ownership next to it because this is a part of the conversation that is more and more in topic, which is who owns the data, right? How was it generated? And we'll speak more of that as we go down this list. So let's assume the data is available. So then what type of data is it? And so remember, alternative data is in reference to a traditional data. And so we've already got an idea of what variables we have been working with. What type of data? Is it image data? Is it text data? What type of storage is it used? Is it flat files? And so on and so forth. And so the aspects of the type of data that are relevant, some of it could be, can we link this data? Can I use this data in a supplementary way for a project and link it to traditional data? Or can I replace the traditional data with this alternative data? And can I create the variables I need for the model perhaps, or however I might want to use it? Another component of or characteristic of alternative data that is relevant is the size. So often we get larger data size sets, but alternative data can also be small. And so in comparison to the data that already exists for a project or a framework or an idea, how does it fit in, and how well does it match? In keeping with the size characteristic is accuracy. You can think of, is there missing data? Are there errors in the data? But you can also think about if my current data is working at a daily kind of rhythm, time scale, if you will. If the alternative data is at a monthly level, how do I incorporate that, and how do I make the scope work? And there's both positive and negative aspects to that characteristic, as well as the others. Another component is bias. There is many ways in which we think about bias, but one of them has to do with weighting as well. And so if going back to the example of if I've got a daily time scale and I'm trying to incorporate a monthly time scale, how might I need to weight that, or how can I balance it so that it's appropriate between the data sets, or to replace the data set, whether it's a supplementary use or a replacement use. A component of that is creation. I love how they all tie in together. What was the alternative? How was the alternative data created? Sometimes we don't know all the details of that. So transparency around how it was created, who created it, where it came from, is very important to think about and to decide if that has an impact on how it's going to be used. One of the examples that I came across, which I thought was really interesting, is the informed gaming, where the example was a financial website, and it talked about credit reporting and how it does matter, like what percentage of your credit is in use, right? Like how much of the available balances on your cards are you using, and that impacts your credit score overall. And so it's quite possible that people are deliberately maintaining certain balances because they want to have impact on their credit score, but that as we take that data out of that context, we no longer can see kind of the patterns that might be within the data from that prior usage. And then lastly on this list is unintended consequences, and that's more of a think about what might be ways in which using alternative data could impact the current framework that I'm working in, the current model that I have in usage. And it could be, again, very positive and not very positive. So it just depends on the outcome, but giving it thought and consideration from the beginning and as we evaluate alternative data. All right. So now that we've talked about different characteristics of data, I want to share with you a project in which we used alternative data, and it was with the Producer Price Index airline team. Currently, they use traditionally collected data to create some indexes, and they wanted to validate replacing that with alternative data. And we had 3 years of historic data, so we generated the indexes to compare against the current airline methodologies for that. A quick shout out to the team. I was not the only data scientist on it. So Gerald Thomas and Stephen Hanna have also been working on the project, as well as the Producer Price Index airline team. Props to everybody. Okay, so one of the reasons that I wanted to share this particular project with you for this is because it's 2 projects. There were 2 different versions of the data over time that we received. And so it's a rich story about using alternative data. So you can see the characteristics that I've just spoken about on the left, and then V1 is version 1 of the data, and then I think about a year later we get version 2 of the data, and so there was that iterative process as well. And so looking at the 2 versions of the data, they were both a third-party purchase from the same source in terms of availability. It was purchased. In terms of type, one of the issues that we came across was that there was no geographical data. And so this is airlines indexes that we're working with. And so we knew that we would need that. Size, they were large files, and the first version of the data was almost twice the size of the second version of the data. In terms of accuracy, or for this purposes, the scope of the data, it was monthly sales transactions based on origin to destination airports. And then another characteristic that came into play was weighting within the data. And so the third-party data source had added a padding of plus or minus 20% to the data, both data sets. But then with version 2 also added a rolling 7-day average to it. So a little bit more complexity in the weighting on that second version of the data. And then, as I said before, it was sales transactions for flights. A very broad look at the project. It was raw data that we started with, filtering out of scope, lots of pre-processing, and then aggregation to the final indexes for comparison. At the bottom, you can see that for version 1, we started with about 120 million rows of data, and through the process of the project, reduced it before the final aggregation to about 50 million rows. Version 2, again, was about half the size of the original raw data, and so we started at about 50 million and ended with about 26 million rows. This is a much more narrowed view of the project. So you can see that there was files that we started with. We added geographic components. There was a lot of ETL that happened. This particular flow appears quite linear in nature, but of course there was a lot of iteration throughout the project, dealing with scope and aggregation, as well as index creation from labeling. So I'm going to simplify this for us, kind of remove some of the that really narrow definitions and talk about those characteristics. And so for data size, again, these were large files that came in for the 3 years of data. And so for each of the projects, we reduced it to, or decomposed the files to yearly files, and then eventually ended up with monthly batches. So 36 files that we iterated over for the processing of the project. In terms of data type, again, geocoding or geolocation was something that we needed to add. So there were resources available to assign airports to country codes, which we did there. And then, of course, testing to make sure that it was correctly labeled for both versions of the data. And then finally, also in terms of the sales transactions, so data creation, accuracy, and bias for the weightings. Those were all components that decisions were made about in terms of the scope, so what was in and out of scope for the data for the project, and how best to aggregate it to create the index creations, the index creations. Again, this was just that full view of all the things that kind of went into the project overall. So when we think about geographic data and the importance of it, it was so within the PPI indexes for airlines, the foreign airport to foreign origin to foreign destination airports is excluded data, so it's out of scope. So that was a huge motivation for finding the geographic data. And then also another component that goes into labeling the indexes or the data for the indexes is whether it's a domestic flight or an international flight. And here domestic would be a domestic origin to a domestic destination for flights. And then cabin classes is another component of it. So looking at how the data was created and then fitting that so that the variables would match up to the index as it's being created, as well as the aggregation decisions and taking into account the weightings for both version 1 and version 2 of the data. Overall, both projects were very successful. For the first 2 rows of this table, that is the 2 indexes that were created, and we're looking at correlations year to year. So this is for an average over 2019 to 2020 and then 2020 to 21. We did have very high correlation with the indexes created from the traditional data is what we're looking at. For the month-to-month correlation, so that's the following 2 rows for the two indexes that were created. Version 1 of the data was a much better higher correlation than version 2, and the rolling 7-day average we think plays a part in that. Looking at the correlations and the creation of the indexes, one thing that was a benefit for using the alternative data was going from a sample of the population to, in essence, a universalness of it, and so a huge jump in data size for the creations. In terms of project outcomes, this is still to be determined whether or not the PPI Airlines team will decide whether or not to put this into production or not. And that's all. Thank you very much.
Thank you, Amy. Our next speaker will talk about candidate work for employers evaluating the expansion of administrative records use beyond non-employer demographic statistics. Will be given by Adela Luque, and she is the Assistant Division Chief of the Business Demographics Applied Research Area in the Economic Reimbursable Surveys Division at the Census Bureau. She leads the research and development of new business demographics data products by leveraging administrative records and census data, including the annual non-employer statistics by demographic series, which is the only official source of demographic information for businesses with no employees in the U.S. She's now leading the effort to assign demographic characteristics to employer businesses, which is the topic of today's presentation. Prior to joining the Census Bureau, she worked at the Urban Institute and as a postdoc fellow and visiting professor in Europe. She received her PhD in economics from the University of California at Berkeley.
Hi, thank you. Can you see my screen? My presentation?
Yes, we can.
Okay, thank you. I cannot see anybody for some reason. And I have too many things open here. I just want to make sure that you see the main page and not like all the different windows that I'm seeing also.
We only see the first slide.
Okay, perfect. All right, I'll just go with that. All right, so thank you, Fane, and thank you everybody for being here today. Today I'm going to be sharing with you some work on a project that seeks to expand to non-employer firms, something that we have already done for firms with no employees, and that is the assignment of demographic characteristics to all employers by leveraging existing administrative records, census records, and third-party data in some cases. I also want to mention that behind this work, there is a great team, as you can see there, and that we have received a lot of great input and support from different parts of the Census Bureau. I also want to thank the Small Business Administration for providing financial support for this work. Okay, and here we have the usual disclaimer. I'm just gonna move on. So as I mentioned, the main goal of this work is to use administrative and census records to assign demographics to all employer businesses. And we already did this for non-employer businesses or businesses that don't have any employees. And because that was successful, it became clear that we needed to try to do this for employer firms. Of course, employer firms are more complex in their ownership structure. So we knew there were going to be a lot of challenges along the way, and we actually didn't know how feasible this would be. An additional objective of this work is to explore alternative ways of demographically classifying businesses that are not based on owners' demographics, but for instance, on the demographics of executives at the firm or board members in the case of public firms. This project has a variety of uses and benefits, including the potential of unburdening business surveys, enhancing existing business programs with demographics, and also enhancing our ability to provide more granularity and flexibility in multiple dimensions, like for instance, more detailed industry and geography, or our ability to drill down into smaller population groups, because we're talking about assigning demographics to all employer businesses and not a survey. The benefits also include reducing costs, facilitating linking business demographics to internal and also external business data and microdata, and improving the sampling frame for business surveys. All right, so let me give you a bit of context and background about how this project came about. So I think we all know by now that in the last few decades, surveys have gone through declining response rates and increasing imputation costs and rates. And at the same time, the demand for more frequent, timely, high-quality data has increased over time. So among other things, the Census Bureau has turned to leveraging administrative records, third-party data to address these challenges, to unburden surveys, and also create new data products with higher frequency and timeliness. So looking at the top box now, the gray box, we see the predecessor of the current business demographics program at the Census Bureau. And that was the Survey of Business Owners, or SBO. As you might know, the SBO surveyed both non-employers and employer businesses every 5 years and provided business demographic characteristics. The last SBO was actually the 2012 SBO, which is over 10 years now. But like I said, there was a need for more frequent data. So the employer component of the SBO was annualized, and that became the annual survey of entrepreneurs. And that later evolved into the annual business survey, or ABS. And that's the light blue box that you see there on the left. So what happened to the non-employer component of the SBO? Well, something to keep in mind is that non-response rates for non-employers, for businesses with no employees, was quite high. It was over, for demographic questions, was quite high. It was like over 50% of non-response. So there, for non-employers, the census decided to leverage administrative and census data to produce demographic estimates for the universe of non-employers, and that's the green box that you see there. That became what is known now as the Annual Non-Employer Statistics by Demographics, or NESD. And we actually managed to release, the first release happened in 2020 during the pandemic with 2017 non-employers data. And that was when the 2017 SBO would have come out. So in this way, through this hybrid approach right now of like survey on one side for employers and AR-based demographics for non-employers, the Census Bureau provides business owner demographics. And that's where we're at right now. So how does this work, this employer demographics work that we're discussing now, fit into this picture? And the immediate plan is to unburden the annual business survey of demographic questions and provide demographic characteristics for employer firms, with some exceptions that I'm going to discuss in a couple of slides. All right, so what data do we use? From the business register, we obtain employer firm identifiers and variables related to businesses like employment, payroll, industry, geography, legal form of organization. Regarding demographic data sources, we get race, Hispanic origin, sex, age of owner, and place of birth from a variety of sources: the Decennial Census data, American Community Service data, the Numiden data from the Social Security Administration. For veteran status, we use Department of Veteran Affairs administrative records data, and we are also planning on incorporating shortly Department of Defense data to supplement VA data. And the business owner identifiers, which we call protected identification keys or PICs, come from income tax data, and I'll talk about that in the next slide. All right, so what's the methodology? How do we go about assigning demographics to employers? The first step is to identify employer businesses, which is already done by a different area of the Census Bureau. So we extract those firms that have been identified as employers from the data based on payroll. Then we need to identify the owners of the firms, of these employer firms, to then link demographics from the various sources that you just saw to them. And for this linking, we use these unique anonymized person identifiers that I referred to earlier, called PICs. That allows us then to link person records across different data sources. So the sources of PICs, which is de facto how we go about identifying business owners, hinges upon the legal form of organization, or LFO, of the firm and the tax forms that they file. So for sole props, the source of PICs are 1040 filings and Schedule Cs. And then we also use EIN applications. For partnerships and S-corps, the source of PICs is Schedule K1 tax data. And for owners of U.S. corporations, that we're basically out of luck, because there is no tax or administrative source that unequivocally identifies all owners of a C corporation in the U.S. So we are looking at different things for different types of C corporations. For instance, like you see there, for small C corporations, we want to impute demographics, and we're also looking into evaluating the feasibility of classifying public corporations demographically based on the demographics of things like executives or board members. All right, so once we have identified the owners, we link demographic characteristics to them using these pegs, as I mentioned earlier. And then we roll up these owner level demographics up to the firm level, because some firms have more than one owner. And we use that using a methodology that is basically a standard methodology that has been traditionally used by the annual business survey and previously the SPO. And that is basically what you can call the majority rule. So if a business is assigned the demographic of the group that jointly owns more than 50% of the business. And a business is eligible for demographic classification if the top owner owns at least 10% of the firm. Otherwise, the ownership is too diffused. And only the top 4 owners are considered for demographic classification, but the vast majority of firms in the US, over 90%, have 4 owners or less than 4 owners. Okay. All right, so how are our results looking? I think they're looking good, especially considering that that in the annual business survey, the non-response rate for demographic questions is about 50%. So, so now we have owner information for about 97% of sole proprietorships, 95% of S corporations, and about 76-77% of partnerships. So overall, we have owner information for about 90 to 95% of non-C corporations, accounting for about 88% of employment, of non-C corporation employment. So we're doing well for non-C corps, but to complete the picture, we should also take a closer look of what we want to do with C corporations, which is a big challenge. All right. So, hold on a second. There we go. And this is what this table is showing. So the row colors are meant to represent how successful we think we can be in assigning demographics to these types of C corporations. That is without a survey. And the darker color, the darker the color, the less successful we think we can be without using a survey. The gray text, as you see there, are things that we are currently working on, but they're not ready to be implemented yet. So overall, C Corps represent about 17% of all employer firms, but account for about half of the employment in the US. Looking at the yellow row now, we see that small C corporations represent about 14% of employer firms, but only 3% of employment. And for those, we think we can impute their demographics. Then in the lighter orange, we have public C corporations, and those represent, but let's put about 1% or less of employer firms, but they account for a big chunk of employment, about almost a quarter. And for those, like I mentioned earlier, we are exploring the use of using third-party data to identify executives, board members, and assign demographics based on the demographics of those parties, executives or board members. And finally, in the dark orange, we have large private C corporations, which represent about a quarter of employment. So they are very important in that respect, even though they only make up about 3% of employer firms in the US. For those, we think that we probably have to rely on the annual business survey to get demographics for them. So that's where we're at with C Corps. And looping back to the original question, can we leverage administrative records, third-party data, to assign demographics to employer firms? And we think the answer is yes, that we can do this for non-C corporations. We think we can model demographics for small C corps. We also think we can find alternative ways of classifying public corporations, and that at this point we think that probably we need to rely on the ABS on a survey to get demographics for private C corps. And that's all I have. I thank you very much, and I look forward to your input and your suggestions. Thank you.
Thank you, Adela. Our next talk is on pulse surveys as a tool for improving survey organizations. It will be given by Herman Alvarado of SAMHSA. Herman is a supervisory social science analyst with the Office of Program Analysis and Coordination at the Center for Behavioral Health Statistics and Quality at SAMHSA. In his role, he is responsible for coordinating support for the center, including the development, implementation, and management of employee engagement activities. Herman has over 22 years of experience in survey research and methodology, in particular data collection and dissemination for the Current Population Survey, the American Community Survey, and the Economic Census. Welcome, Herman.
Thank you very much. I really appreciate it. So today we're going to talk about pulse surveys as a tool for improving surveyor organizations. First of all, I would like to acknowledge my colleagues from SAMHSA, Kathy Piscopo and Michael Inguillo, who helped me to develop this presentation. If we take a look at the title of the presentation, there are two topics here. First of all, we're going to talk about pulse surveys, but most importantly, it's about improving survey organization. So this is going to be from a business perspective, mostly about the staff engagement, employee engagement, and also organizational improvement. So, second. Okay, let me go back here. For some reason, this screen is not showing. Okay. So what are pulse surveys? Pulse surveys are technically a short set of questions. They're basically about one or more
Herman, we
topics.
can't see your screen. I don't know if I'm the only one, but I don't see your screen.
Let me try something again. Hold on one second. Let me just Can you see it now?
Yep, we can see it now.
Thank you. Okay, so going back. So what are pulse surveys? It's about a short set of questions that are about even one or more topics, but we try to keep it short. This could be about emerging issues or follow up on some focus areas. As we're going to learn, you can do more than one pulse survey just to follow up on some of the topics or some of the themes that you have identified. And they can be used in different contexts. We know about the household pulse survey from Census. And as we mentioned, we're going to focus on employee pulse surveys. So what is an employee pulse survey? There's a definition here about, it's kind of like it's a method used by organizations to gather feedback and insights from their employees. It involves administering a set of questions or statements to employees to gauge their perception, satisfaction, and engagement levels within the workplace. A mouthful. So technically, when we're talking about employees' pulse surveys, we're talking about engagement surveys. So what are some of the characteristics of employee pulse surveys? They're short and easy to respond to. Frequent administration. It could be like every month. It could be every quarter. It could be every 6 months. It's determined by management about how frequent they want to be implemented. It's an easy to reach audience. You don't have to go to some organization, external organization, to get a sample frame. The sample frame, we have it within our group, within our organization. So it's easy to get a list of the employees. And the goal is to provide that immediate snapshot of employee opinions and experiences. And also the frequency allows building comparative data and identification of potential trends within a time frame. There are some benefits about pulse surveys. One of them is provide information on hot topics or reactions to recent organizational events, like a reorg in any organization. Also, it helps leadership to get involved on what we call continuous listening efforts. And most importantly, what we call increased connectivity. And with that, when we hear that phrase, change is the only constant in every organization, that's what we're talking about. As we move through all these phases of change, employees want to feel that they're connected, that they provide feedback, and those that input that they provide is incorporated as part of the changes. So that can increase the acceptance of organizational, environmental, and administrative changes within the organization. However, there are some risks associated to pulse surveys. One of them is the over-surveying and survey fatigue. Okay, we're talking about the frequency. Sometimes it's too much. Also, as you know, there's so many software out there that that build surveys. So it's becoming more and more popular to do surveys in the organizations. So we may have some people that might be like developing questionnaires without necessarily the necessary set of skills or the knowledge on survey methodology, or not even a background in survey methodology. So that can lead to poor questionnaire design. And we know questionnaire design can lead to poor information. Also, the perception that the focus of the survey is on tracking if things are being done rather than action and change, especially when some pulse surveys, they have information like instructions about, we're going to provide, please, we need this, your information to make changes, but then when you look at the questions, it's all check marks, like check, check, check. So it raises suspicion that it might be more about tracking rather than doing something concrete. And also the accountability that is not always clear. And in this case, for example, if the survey comes from HR, who's going to be the one making the final decisions? Is it HR just collecting information that is going to be passed to management, or this is just HR just collecting information? So sometimes accountability is not that clear. So I'm going to provide an example, and this is from our survey organization, which is the Center for Behavioral Health Statistics and Quality, also known as CBISC, at the Substance Abuse and Mental Health Services Administration, SAMHSA. CBISC is a federally recognized statistical unit by OMB, and we collect, analyze, and report data on substance use and mental health disorders, different types of data, multiple data collections, and the most, probably the one that most of you are familiar with, is the NISDA, which is the National Survey on Drug Use and Health, which is an annual survey that is conducted by SAMHSA every year, but we have other surveys and data collections that are also part of the portfolio of data from SAMHSA. What is important about CIBISC is a small unit of about 70 people right now. And we're a mix of statisticians, health professionals, behavioral scientists, social science analysts, program analysts, survey researchers, and other professional areas. And we all have different levels of experience working in different work settings. And one of the things that we found is like about 30% of the people that have joined recently, our staff, they're brand new to the federal government. So given that information, I'm going to provide you some examples of how we have used pulse surveys in SAMHSA CIBISC. Again, these are examples. There are so many instances that you can use pulse surveys. I'm just going to provide you just a few examples of these. One of them is to gather information on training and work support. This is a survey that we conducted back in November of 2022. It was a pulse survey. And as you see in this question, we asked about a series of brown bags that we were scheduling. And we have identified already the topics. We just wanted to know like which ones had more interest in staff in terms of like which ones we would schedule first, which ones really had interest, which ones really didn't have interest. And also we have another question about other activities that could help to support the work of staff. Also, we use it to identify or to ask for specific details on workplace issues. As we know, when we have a categorical question, sometimes the categories don't say that much. So sometimes we need staff to provide us more details. So in this case, this is a pulse survey that we conducted last year, and we asked about, do you feel comfortable approaching CIBISC leadership with your issues and concerns? And we asked why or why not. Another question was like, do you feel that the CIBISC leadership has been responsive to your issues and concerns? Why or why not? And it was just a matter of a staff providing details or specifics about their responses. Also, we used pulse surveys to collect information in preparation for a meeting or event. For example, at SAMHSA, we have a core community of practice, core meaning contracting officer representative. And just this past January, we were having a meeting about the requirements for recertification. So this is a 45-minute meeting. We knew there will be a lot of questions, so we wanted to make sure we were addressing their questions and that we were addressing the what they need. So one of the questions was like, how far are you in the process of getting recertified or certified? So we had the categories there. And also it's like, what questions do you have for blank? I mean, for obvious reason, I didn't provide the name of the person, but it's basically our core coordinator. And she was basically responding to some questions, and we wanted to, in advance, to give her a list of these questions. So based on what they provided us, we were able to actually like get those questions, identify which ones were kind of like duplicate, and identify some topics that will be very helpful to lead the discussion. And another instance, another example is the follow-up to a major meeting or event. This is, again, for the core community of practice. We had a meeting back last year. It was our kickoff meeting. And we follow up with some questions about like, will you be interested in being part of the mentoring program? We provided the definition. And then for those who say like they wanted Do you want to be a mentor, or are you seeking for a mentor? So this is information that is helpful for us, as we already provided some information about the mentorship program. So how pulse surveys improve organizations? In the case of CIVISC, it helped us, for example, for meeting and events, to establish priorities. And as I mentioned, when we gather questions or topics, we can actually group them, and that will help to lead the discussion. For management, it helps to establish priorities, identify training needs, any pressing issues that must be addressed, for example, building morale, programs or operation improvement, identify areas for growth, and connect feedback with concrete actions. So what are some of the lessons learned as we have been implementing these pulse surveys? And again, this is from the staff engagement and organization improvement perspective. So some of the lessons that we have learned in the last year and a half that we have been implementing this in our units. First of all, the software selection. There's so many software out there, so you need to make sure that your software meets the needs of what you want. For example, in our case, we wanted surveys that we were able to have skip patterns, that if there was something that needed to be, that the text was wrapped around, and that it was easy to distribute, and also monitoring, that we were able to see the analytics in real time. But again, there's so many software out there, like SurveyMonkey, Qualtrics, Crazy Egg, Google Forms, Microsoft Forms, Question Pro. So make sure that you identify what are the needs of what you need before you actually do the software selection. Also, do not expect 100% response rate, even though are the employees, these are your people. Not everybody is engaged, or not everybody wants to respond, or sometimes the specific topic of the survey is not of their interest. One example is like when we were doing the one for the core community of practice, not everybody's a core. So they're going to say like, why should I answer this? Another lesson that we learned, even when poll surveys are anonymous, some staff may still have confidentiality concerns. And that happens especially when they're like open-ended questions. They feel like, well, if I write too much, they might probably be able to identify who I am. Or sometimes if you ask for demographics in those poll surveys, they might feel like, wait, I mean, if I, like in my case, for example, who's the only male Hispanic supervisor in my group? Only me. So it might be like, well, maybe if they ask too many demographics, they might be able to see who I am. So there might be some confidentiality concerns. Also, the risk of that respondents will avoid or ignore open-ended questions, maybe because they feel like I don't have the time to write, or I don't have the time to expand on this, or maybe if I say too much, they might be following up. So, I mean, there might be so many possible explanations for this. And very important, always test every version before launching. Sometimes as we're building the poll survey, I don't know, maybe a grammar error or some formatting issue. Let's go back to the programmers. And sometimes it's even sometimes like a dot or a comma that was missing. Even if it is a minor comma, when it comes back, test it, because with some of this software, just one minor change that you make, it might trigger some other effects. So always test, because you never know. Okay, so with that said, this is the presentation, short and sweet in terms of like giving you an overview of poll surveys. So here's my contact information in case you have any questions. Thank you.
Thanks, Herman. All right, so our last talk of the day, talk about record linkage. So easy topic. To introduce our speakers, Dr. Corey Sparks is a senior research scientist at the Coleridge Initiative. Corey is an applied demographer and quantitative methodologist with research interest in health disparities, spatial analysis, and educational disparities. Corey earned his PhD in anthropology and demography from the Penn State University. And his other speaker is Katerina Levitskia, is a senior data scientist at the Coleridge Initiative. Her work is focused on working with government agencies to apply computational approaches and help develop analytical pipelines and data products. She earned her Master's of Science in Applied Urban Science and Informatics from New York University and Master's of Arts in Computational Linguistics from the City University of New York.
Thanks, Wayne. Nice to see everybody. I'm glad to be invited. We got to come to FedCASIC and talk about this recent work that we're doing with National Center for Science and Engineering Statistics. We call it Striking Gold, using public sources to validate a gold standard data set of PhD inventors in the U.S. Next slide, please. Next slide. So just to start with, this work was supported by NCSES and NSF. Everything that we're saying here are our views. They're not necessarily those of NCSES or NSF. The data that we're talking about today is a demonstration pilot project, and it's not currently available for public use or external distribution, although we'll talk more about that towards the end of the presentation. Next slide. So what is the gold standard data set? What are we referring to when we talk about a gold standard? Most of us, or many of us on the call here, are statisticians in some way or another. And how many times do we really get to say with 100% certainty that we know the truth about something? Everything's always an estimate. Uncertainty is everywhere in our work. The gold standard data set is really something that can be considered a ground truth version of some sort of data that you're working on. This is where outcomes are 100% known for the sample that you're dealing with, and the uncertainty about membership or value of the outcomes or predictors, any part of the data, is minimal or in fact zero. There are some good examples from the computer science literature and other areas that have used gold standards to proof machine learning models and things like that. And so this is not necessarily a new concept, although it's not used very often in the social science world or within the fields that many of us work within. Next slide, please. So in terms of a record linkage project, how do we use a gold standard data set? Record linkage is usually linking some form of administrative data to another form of administrative data or to a survey data set. And it's becoming increasingly used to generate evidence to inform all kinds of decisions that affect public policy, service utilization, et cetera, et cetera. A lot of our work at Coleridge Initiative focuses on linking different administrative data sources together to inform these areas. In terms of a gold standard, this is where the data match have a confirmed match status of records. So we know records from one data set are 100% known to be in another data source. These are known status individuals who've been validated through one of many different types of methodologies, so that we know that there's not a variance in terms of their matching. They are the same people in multiple data sources. Next slide, please. So this project is describing the linkage project between linking doctoral recipients to inventors based off U.S. doctoral recipients. This is unfortunately there's not a single large-scale data set that links the U.S. doctoral workforce to inventors that's available. A data set like this could be used for a lot of different ways, really just studying how the innovation process within the United States and even internationally, because we can see if individuals in the data are located in a foreign country when they patent. So there's a lot of different ways you can use this, but really it is looking at this process and inequalities in this process of patenting that unfolds after people receive their PhD. How does that work? What we're doing here is we've developed some machine learning models to link two data sources. First is the survey of doctoral recipients, or SDR, which is a biannually collected survey of people with PhDs. It's longitudinal, collected by the National Center for Science and Engineering Statistics. And the patents view data, which is a public data source, which disambiguates inventors and tracks them throughout their entire patenting history in the United States. That's collected by the U.S. Patent and Trade Office. Validation of how the machine learning model works is we're doing this, we can fit our machine learning models, but then we're using them as a test set on this gold standard to ground truth our models and make sure that they're performing well. And with this gold standard, then you can see this with great success because you have this really ground truth version of the data. Next slide, please. The two data sources we're talking about here are the Survey of Doctoral Recipients, or SDR, and the Patents View. The survey is collected by NCSES and has been for a long time, since 1973. What we're using here is a panel of the data that were they were in the survey between either 2015 and 2017. They could occur in both years, but they have to be in at least one of these. And the survey has changed over the course of its collection, and previous rounds of the survey included questions on patenting activities of the respondents in previous survey cycles. Although the questions related to this were removed in the ways that we're using, we can actually follow people back in time and see if they had a positive response for having patented something. So the good thing about the SDR is each respondent has a unique identifier, which you can track them over time. The Patents View is a public data source on every patent from 1976 to the present. The version of the data that we're using for this was up to date through, I believe, Q2 of 2023, and it's from the U.S. Patent and Trademark Office, USPTO. What this data contains it's a lot of information on inventors, who they are, where they are when they're patenting, their assignee, or potentially the organization they were working for during the time they were submitting the patent, dates of patenting application, dates when the patents were granted, and other variables about team composition, citation levels for the patents that we can link together in a relational database kind of structure. Next slide, please. So who can we try to link together in these two sources? So this is sort of a Venn diagram of people that are in the SDR in this biennial round that we're using, and we have all the people who applied for patents in the United States during the same amount of time. So what we're able to try to get at in this project is that slice of these two populations that overlap: inventors who patented in the U.S. with a doctoral education from a U.S. institution. So again, a lot of times when you're doing a linkage project, you have to focus on the donut and not the whole. So you think about, well, what can we learn about this portion of this doctorally educated workforce and their patenting activities and variants in that. I'll turn it over to my colleague Ekaterina and let her talk.
Like Corey was saying, for our recognition project, we really needed to identify a gold standard data set so that we know how well our model behaved and how well it predicted the results. And so in our case, again, like Corey mentioned, the true positive, so a pair of records that is a true match, would be the doctoral recipient, who we know for sure was an inventor that we found in the public data source. And so for the true negative match, that would be the doctoral recipient for whom we definitely know there is no corresponding inventor record. So we know for sure that they're not inventors. And so what we did here, so using this alternative data source, we thought about using public resume data, because what we have in the resume data is we have the full name of the person, we have the first, last name, people usually include their graduation institution and when they graduated from a specific institution. And you would expect that people who patent, you would expect that quite often they would mention the patent number in their resumes. And so here, this is kind of the key diagram we have here to explain how we created our gold standard. And by linking the resume information on the left-hand side to the public inventor data, so we linked it on the first and last name and also on the patent number. And to us, that is a pretty high confidence match because usually patents do not have too many inventors. So it's very highly unlikely that you get the same person with the same name on the same patent number. So to us, that was a high confidence match. And on the right side, we connected the same resume to the person SDR, again, using the first last name. And then we used the PhD graduation institution and the year of the PhD graduation to confirm that indeed we're looking at the same person. So the resume data was the key link here for us. And on this, we based our gold standard data. So now we will quickly describe what is the sources of public resume information we've been able to find online, and we hope that it might be helpful for others who are looking for this type of alternative data sources. The first one we'll talk about is LinkedIn. So of course, probably most of you, when you think of what is the data source where there's a lot of resume information, we think of LinkedIn. And indeed, it was a very helpful source for us. So in LinkedIn, you can get the full name, the first, last name of the person. And here I highlighted the other elements that we were able to scrape. So the university name of the person, where they graduated from, also the level, confirming that they indeed received their PhD degree, and also the year when they graduated. And also we were looking specifically for profiles which had in the same profile the mention of the patent number. So we know for sure that this is the same person we're looking at when we go into patent data and the SDR data. So LinkedIn is a wonderful source. However, quite a big con is that it does not have a formal API. So we actually had to do the search manually. And we were able to semi-automate this, but still, it's a pretty manual and laborious task. And sometimes if the same profile has multiple pages with a long list of patents, you kind of have to go through additional steps there. But it was a really good source for us. Another one that we want to highlight is the ORCID. Probably most of you who work in research know about this source. So this is where a lot of researchers post their, again, resume information, and it includes the profile name, their education qualifications. In the work section, quite often you can see the mentions of the patent numbers. And so this is what we needed for our project. And they also quite often cite the funding grants. The grant numbers were also very helpful for us because patents do often cite the grants. And through the grants, we could link people to inventor data as well. So this was another good source for us, and a big pro here, they do have formal API, so application programming interface, so you can programmatically quite easily download this information. So it was completely automatic process for us as opposed to LinkedIn. However, ORCID doesn't have as wide reach as LinkedIn. It can be a little bit more skewed towards the research population, but because in our case, we were dealing with doctoral recipients, that was a very good source for us. Another source is public that we looked into in terms of the resume information is the ResearchGate. Probably most of you know about this source. It was a good source in the sense we could get the first and last name, we could get the patent numbers. However, people don't always post their education information. They don't always post their company affiliations. So you see the key elements that we needed in terms of graduation institution and graduation year were quite often missing. So it wasn't a perfect source for us. And there's also no formal API. Another source, which probably also most of you know, is the Google Scholar. same like with ResearchGate. People do post their patent numbers there, so you can find people online. But again, they do not post often their education information. There is an option for that, but it's quite often missing, as well as company affiliation as well. So it wasn't perfect source, and the API here was missing as well. And one last source that we looked into was the postjobfree.com. And for those of you, it might come handy. What they do is it's actually about several millions of public resumes online that are being posted. So people upload there, and there's a disclaimer that they have no rights to this. They know that it's for public use, and they're happy with it being used. However, big caveat here. As you saw previously, the other websites, they do have structured data, but this is completely unstructured data. So it's just a text file, and you have to go extra steps to parse it. And that's much more laborious. But we still wanted to mention this as a potential source for anyone who's interested. That's my timer, 15 minutes. Okay, we're almost there. So to summarize, this using those the public data sources that we just mentioned, we were able to confirm about 117 SDR respondents. We were able to successfully link, and so with the resume data, and confirm that indeed these SDR doctoral recipients were the inventors. And with about 1,311 inventors, we did confirm them to not have PhD education. And however, we do want to caveat that this is based on what they report, right? Could be a self-reporting issue that they perhaps did not report that they received PhD indeed. So just to quickly summarize, we think that was for us a really good proof of concept that the gold standard data can be created using public resume information. It avoids the responder burden. And finally, this type of public information, it's easier to be accessed by the research community and easier to be shared. But some of this data is highly unstructured and could involve some extra steps to be processed. And I'll finally turn it over to Corey for the next steps.
So what's next with this, and what kind of potential applications can we think of? We are having a linked data product that we are producing off this. It will be public use. It's currently under review by NCSES. Behind this, we're going to be sponsoring a data fest and a training course starting in about a month using this data. So if you're interested in this, you can check our social medias to see how to apply for that. And there's a lot of potential outcomes. You could look at this from a research context. You could look at diversity of inventors. You could look at citation of patents. You could look at federal funding and how that translates into citations and use of patents. And then how patents potentially affect career trajectories of those with PhDs in the workforce. So again, this, like a lot of the data sets we've talked about in the session today, they're novel, and we can't answer novel questions without novel data. So this is one of the things that we're doing at Coleridge that's driving this. Next slide, please. So thank you. If there's any questions, you can type them in the chat, and you can find us on LinkedIn as well as on the web. Thank you for your attention.
All right, thanks everybody. So some interesting talks. It is at the end of the day. I know. So we'll see how many questions we get, but there is a few minutes left. If someone would like to ask a question, you can put that in the chat or raise your hand. Any questions? I have some, but since we're so close to the end, I think I'll just give the audience a chance and hold off on mine. Um, all right. One last call going once. Going twice. I don't. Oh, we do have one question in the chat. I see. Okay, for the last talk, would you be able to scrape data from LinkedIn?
Yes, thank you for the question. I would really caution of scraping in an automated way from LinkedIn because LinkedIn did sue people who did so, and please do not do that. They have an official disclaimer that any automatic bulk sort of downloads and any sort of automatic scraping is prohibited. So that's why we did sort of a manual search and manual looking up. But we do recommend to use ORCID instead because they do have official API and it's officially permitted there. That would be our recommendation.
All right. Well, I think you have contact information for the authors in case there are any additional questions, but we're at 5:45, so we'll go ahead and wrap up. Thank you very much to everybody who participated today in the audience, and see everybody tomorrow. Thank you.
Thank you, Fane.